Every large galaxy harbors a supermassive black hole at its center, an invisible monster containing millions to billions of times the Sun's mass compressed into a region smaller than our solar system. The Milky Way's central black hole, Sagittarius A-star, weighs 4 million solar masses and sits 26,000 light-years from Earth at the galaxy's heart. Despite this enormous mass, Sgr A-star's event horizon, the boundary beyond which nothing escapes, spans only 12 million kilometers, roughly 17 times the Sun's diameter. The supermassive black hole in the galaxy M87, imaged for the first time by the Event Horizon Telescope in April 2019, dwarfs Sgr A-star at 6.5 billion solar masses, with an event horizon 38 billion kilometers across, larger than our entire solar system. The most massive known black hole, TON 618, contains 66 billion solar masses, 16,000 times more massive than Sgr A-star, lurking 10.4 billion light-years away in a quasar so luminous it outshines a trillion suns. Supermassive black holes weren't always this massive. They formed through processes still debated by astrophysicists. One scenario involves direct collapse of massive gas clouds in the early universe around 200 million years after the Big Bang. If a primordial gas cloud exceeding 100,000 solar masses collapsed rapidly without fragmenting into stars, it could form a black hole seed of 10,000 to 100,000 solar masses. These seeds would then grow through accretion, consuming surrounding gas and stars, and through mergers with other black holes as galaxies collided over billions of years. Another formation channel involves stellar remnants. The first generation of stars, formed from primordial hydrogen and helium, grew far more massive than modern stars, perhaps 100 to 1,000 solar masses. When these giants died, they collapsed into black holes of 10 to 1,000 solar masses. These stellar mass black holes sank to the centers of their host galaxies and merged, building supermassive black holes through hierarchical growth over cosmic time. The correlation between black hole mass and galaxy properties reveals deep connections between black holes and their hosts. In 2000, astronomers discovered the M-sigma relation. Supermassive black hole mass correlates tightly with the velocity dispersion sigma of stars in the galaxy's bulge, the central spherical component of spiral galaxies, or the entire body of elliptical galaxies. The relationship is M equals approximately 100 million solar masses times sigma divided by 200 kilometers per second to the fifth power. This means galaxies with faster moving stars in their centers host more massive black holes. The correlation extends over 5 orders of magnitude, from black holes of 1 million solar masses in small galaxies to 10 billion solar masses in giant ellipticals. This tight relationship suggests black holes and galaxies co-evolve. Black hole growth regulates galaxy growth through feedback, while galaxy mergers feed black holes and trigger growth. The discovery of supermassive black holes unfolded over decades. In 1969, Donald Lyndon Bell proposed that quasars, extraordinarily luminous objects, billions of light-years away, were powered by accretion onto supermassive black holes. At the time, black holes were theoretical curiosities predicted by general relativity, but not yet observed. In 1971, observations of the X-ray binary Cygnus X1 provided the first strong evidence for a stellar mass black hole, about 15 solar masses, accreting matter from a companion star. By 1974, radio astronomers identified Sagittarius A-star as a compact radio source at the Milky Way center, over subsequent decades. Tracking stellar orbits around Sgr A-star using telescopes like the Keck Observatory and Very Large Telescope revealed that stars orbit an invisible mass of 4 million solar masses concentrated in a region smaller than Mercury's orbit. This provided definitive proof that Sgr A-star is a supermassive black hole. Measuring black hole masses requires observing how their gravity affects nearby matter. For Sgr A-star, astronomers track individual stars orbiting the black hole with periods as short as 16 years for the star S2, which passes within 17 light hours of the event horizon at speeds exceeding 7,000 kilometers per second, nearly 2.5% the speed of light. Applying Kepler's laws to these orbits yields the black hole's mass with precision better than 10%. For distant galaxies, astronomers use different techniques. Measuring the velocities of stars or gas clouds orbiting the galactic center using spectroscopy, splitting light into constituent wavelengths, and measuring Doppler shifts reveals the central mass. Alternatively, reverberation mapping for active galactic nuclei measures time delays between variations in the accretion disk's brightness and echoing emission from surrounding gas clouds, constraining the size of the emitting region and, combined with velocity measurements, yielding black hole mass. Not all galaxies host supermassive black holes of similar mass relative to their size. Spiral galaxies, like the Milky Way, have black holes comprising roughly 0.1% of their bulge mass. Giant elliptical galaxies often have black holes reaching 1% or more of total galaxy mass. Dwarf galaxies contain intermediate mass black holes of 10,000 to 1 million solar masses, though some appear to lack central black holes entirely. The scatter in the M-sigma relation suggests that galaxy mergers, gas accretion, history, and environmental factors all influence final black hole mass. Understanding this diversity requires studying black holes across cosmic time, observing how black hole populations evolve from the early universe, where quasars with billion solar mass black holes existed when the universe was less than 1 billion years old, to today's quiescent supermassive black holes like Sgr A-star that accrete minimally. Supermassive black holes influence their surroundings profoundly, despite their compact size. Sgr A-star's gravity dominates within about 3 light-years, influencing stellar orbits and dynamics of the central parsec. Beyond this, the galaxy's distributed mass of 200 billion stars dominates. But when actively accreting, supermassive black holes become quasars, or active galactic nuclei, releasing enormous energy that affects entire galaxies. Radiation from the accretion disk heats surrounding gas to millions of Kelvin. Powerful winds driven by radiation pressure expel gas at thousands of kilometers per second. Relativistic jets launched along the black hole's spin axis carry energy across hundreds of thousands of light years, depositing heat in the intergalactic medium and regulating cooling flows in galaxy clusters. This feedback shapes galaxy evolution, quenching star formation, and determining the final properties of massive galaxies observed today. The existence of 6 billion solar mass black holes, like TON 618, poses theoretical challenges. Such enormous masses require either very efficient accretion or numerous mergers over cosmic history. Accretion is limited by the Eddington rate, the maximum rate at which a black hole can accrete before radiation pressure from the accretion disk halts further infall. For a 1 million solar mass black hole, the Eddington limit is about 0.2 solar masses per year. Growing from 100,000 solar masses to 10 billion solar masses at the Eddington limit requires roughly 1 billion years. Yet quasars with billion solar mass black holes existed when the universe was only 700 million years old, leaving insufficient time for Eddington-limited growth from stellar mass seeds. This suggests either black holes formed from more massive seeds, perhaps 10,000 to 100,000 solar masses, through direct collapse, or super Eddington accretion occurred, exceeding theoretical limits through radiation trapping in thick disks or other exotic mechanisms. Supermassive black holes are fundamentally different from stellar mass black holes, not just in mass, but in observable properties. Stellar black holes form from individual star collapses and have masses ranging from 5 to 100 solar masses. Their event horizons span tens to hundreds of kilometers. Tidal forces at the event horizon are enormous, exceeding billions of Earth gravities, instantly spaghettifying any object crossing. Supermassive black holes have event horizons millions to billions of kilometers across. Tidal forces at the horizon of a billion solar mass black hole are only a few Earth gravities an astronaut could cross the horizon without immediate distress, though they would inevitably be crushed approaching the singularity. This means infalling matter near supermassive black holes can remain intact much longer, forming extended accretion disks and producing different observational signatures than stellar black holes. When two galaxies collide, their supermassive black holes eventually meet. This process unfolds over hundreds of millions to billions of years, beginning when galaxy disks first overlap and ending when the black holes themselves merge in a catastrophic coalescence lasting milliseconds. Understanding supermassive black hole mergers requires tracing the full evolution from galactic collision through gravitational inspiral to final plunge and ringdown. Each phase produces distinct observational signatures from disturbed galaxy morphologies and dual active galactic nuclei to gravitational waves rippling through spacetime. These mergers represent some of the most energetic events in the universe, releasing more energy in seconds than all stars in the observable universe emit over the same time. They reshape galaxies, influence cosmic structure formation, and provide unique laboratories for testing general relativity in extreme regimes inaccessible by any other means. How galaxy mergers bring black holes together. Galaxy mergers are common in the universe's history. Observations reveal that most massive galaxies experienced at least one major merger collision with a galaxy of comparable mass and numerous minor mergers with smaller galaxies over the past 10 billion years. The Milky Way is currently colliding with the Andromeda Galaxy, closing the 2.5 million light-year gap at 110 kilometers per second. First contact will occur in approximately 4 billion years, when the galaxy's disks begin interpenetrating. Over the next 2 billion years, the galaxies will pass through each other, separate, fall back together again through mutual gravitational attraction, and eventually merge completely around 6 billion years from now. The merged remnant, nicknamed Milky, will be an elliptical galaxy with the combined mass of both spirals, roughly 2 trillion stars. The supermassive black holes, currently 4,100 million solar masses, will sink to the merged galaxy's center and eventually collide. Ongoing galaxy mergers provide snapshots of different merger stages. NGC 6240, located 400 million light-years away, is a merger in progress, showing 2 bright nuclei separated by about 3,000 light-years. X-ray observations by the Chandra X-ray Observatory revealed that both nuclei host active supermassive black holes, a dual-active galactic nucleus system where both black holes are actively accreting gas and producing X-ray. Emission. The black holes have masses approximately 100 million solar masses each. They orbit each other with a period roughly 100 million years, slowly spiraling inward as the merger progresses. The galaxy shows intense star formation at a rate exceeding 100 solar masses per year, 100 times the Milky Way's current rate triggered by gas compression during the collision. NGC 6240 represents an intermediate merger stage, occurring roughly 500 million to 1 billion years after initial galactic contact. The antennae galaxies, NGC 4038 and NGC 4039, display spectacular tidal tails extending 300,000 light-years streamers of stars, gas, and dust pulled out by gravitational tidal forces during the collision. Located 45 million light-years away, these galaxies collided about 600 million years ago and are now merging. Hubble Space Telescope images reveal over 1,000 bright young star clusters formed during the merger, with ages ranging from 1 to 100 million years. The clusters contain millions of stars each, formed when giant molecular clouds, gas clouds, hundreds of light years across, collided and compressed during the merger, triggering gravitational collapse and star formation. The antennae's supermassive black holes, each roughly 100 million solar masses based on galaxy properties, currently sit at the centers of their respective galaxy cores, separated by tens of thousands of light years. They will take hundreds of millions of years to spiral together. Dynamical friction brings black holes together during mergers. As a massive object, like a supermassive black hole, moves through a background of stars and gas, gravitational interactions transfer momentum. Stars passing behind the black hole are gravitationally accelerated, gaining velocity in the black hole's direction of motion. Conservation of momentum requires the black hole to slow down. This braking force, called dynamical friction, was first calculated by Subrahmanyan Chandrasekhar in 1943. The friction force depends on the black hole's mass m, velocity v, and the density and velocity dispersion of the background material. The mathematical form is approximately proportional to m squared divided by v squared times the background density. Importantly, friction increases with black hole mass, meaning supermassive black holes experience stronger friction than stellar mass black holes, causing them to sink to galaxy centers efficiently. The timescale for dynamical friction to bring black holes together varies with galaxy and black hole properties. For 2100 million solar mass black holes in a galaxy with stellar density, 100 solar masses per cubic parsec, and velocity dispersion 200 kilometers per second, the friction timescale is approximately 100 million to 1 billion years to bring the black holes from initial separation of 100,000 light-years to separations around 1 to 10 light-years. Massive black holes in dense stellar environments experience faster in spiral. Low-mass black holes in diffuse environments take longer. Gas friction drag from the interstellar medium can accelerate in spiral if significant gas is present, as in gas-rich galaxy mergers. Observations of dual-active galactic nuclei at separations 3,000 to 30,000 light-years confirm that dynamical friction operates as theory predicts, bringing black holes together on timescales consistent with calculations. Tidal forces during galaxy mergers profoundly affect galaxy structure. As two galaxies approach, each raises tides on the other through differential gravitational pull. Nearer regions feel stronger gravity than farther regions. These tides pull stars, gas, and dark matter out of galaxies, creating tidal tails and bridges visible in deep images. The antennae galaxy's 300,000 light-year tails formed this way. Computer simulations following millions of particles representing stars and dark matter reproduce observed tail shapes, confirming tidal origin. Tidal forces also funnel gas toward galactic centers. During close passages, shocks in colliding gas clouds dissipate orbital angular momentum, causing gas to fall inward. This gas reaches the central regions, fueling starbursts and feeding supermassive black holes, triggering active galactic nucleus activity that might otherwise remain dormant. Hubble Space Telescope surveys catalogued over 100 merging galaxy systems at various stages. The Mice galaxies, NGC 4676A and 4676b, show long, thin tails resembling mouse tails. The Tadpole galaxy, UGC 10214, has a 280,000 light-year tail created by interaction with a smaller galaxy. These systems span merger timescales from initial contact through final coalescence. Statistical studies find that roughly 5 to 10% of massive galaxies currently show signs of ongoing major mergers, implying typical galaxies experience major mergers every 10 to 20 billion years on average. Since the universe is 13.8 billion years old, this suggests most massive galaxies experienced at least one major merger. Minor mergers with smaller galaxies are more frequent. Massive galaxies accrete satellite galaxies continuously, occurring several times per 10 billion years. Gas dynamics during mergers differ from stellar dynamics. Stars rarely collide during galaxy mergers. Typical stellar separations are light years, while star sizes are tens of millions of kilometers, making collisions extraordinarily improbable even when galaxies interpenetrate. Stars pass through each other's galaxies like ghosts, affected only by collective gravitational fields. But gas clouds collide directly. When two giant molecular clouds from merging galaxies collide at velocities hundreds of kilometers per second, shocks compress the gas, heating it to millions of Kelvin and creating visible emission. These shocks also trigger gravitational instability. Compressed gas reaches densities where self-gravity overwhelms pressure, causing collapse into stars. This explains the intense starburst activity in merging systems, producing new stars at rates 10 to 100 times higher than quiescent galaxies. The final stages of galaxy mergers create elliptical galaxies, smooth, featureless stellar distributions with little gas and minimal ongoing star formation. Observations and simulations both show that major mergers between two spiral galaxies of comparable mass produce elliptical remnants. The spiral's rotating disks, supported by angular momentum, are destroyed during the violent merger. Tidal torques and gravitational stirring randomize stellar orbits, converting ordered rotation into random motion. The remnant is pressure-supported stars move in all directions with no net rotation, creating the smooth elliptical structure observed. Supergiant elliptical galaxies like M87, containing trillions of stars and 6.5 billion solar mass black holes, formed through multiple major mergers over billions of years. Accumulating mass and growing central black holes with each merger, understanding when and how black holes first approach each other during mergers requires mapping the merger's timeline. Initial galactic contact occurs when disks first overlap, typically at separations around 100,000 to 300,000 light-years, depending on galaxy sizes. Tidal tails begin forming immediately as tidal forces extract stars and gas. First pericentric passage, closest approach, occurs after roughly 100 million to 500 million years, depending on initial velocities and trajectories. During pericenter, interactions are strongest, triggering starbursts and funneling gas towards centers. After pericenter, galaxies separate, moving apart to distances exceeding their initial separation before falling back together for a second passage, 500 million to 1 billion years later. Multiple passages occur, each further mixing stellar populations and dissipating orbital energy through tidal interactions and dynamical friction. Eventually, typically 1 to 2 billion years after first contact, the galaxies coalesce into a single merged system, and black holes begin the long spiral toward eventual collision. The gravitational dance before collision. Once galaxy merger brings two supermassive black holes to the merged galaxy center, they form a binary system and begin a gravitational dance that will eventually end in collision. This binary spiral occurs through three distinct phases, each dominated by different physical processes. The initial phase covers separations from 30,000 light-years down to about 30 light-years, governed by dynamical friction with stars and gas. The intermediate phase from 30 light-years to about 0.03 light-years, 1 parsec, or 3.26 light-years, involves gravitational scattering of individual stars through three-body interactions. The final phase from 1 parsec to merger is driven by gravitational wave emission, where the binary radiates energy as space-time ripples, causing orbits to decay rapidly. Each phase has characteristic timescales ranging from millions to billions of years initially, accelerating to milliseconds in the final moments before horizons merge. The initial separation of 30,000 to 100,000 light-years occurs immediately after galaxy merger completes. At these scales, the black holes haven't yet formed a true binary. They orbit within the merged galaxy's potential independently. Dynamical friction dominates their evolution. As each black hole moves through the stellar background, gravitational interactions with stars transfer orbital energy to stars, slowing the black holes and causing them to spiral inward. The friction timescale depends on black hole mass, stellar density, and velocity dispersion. For 2,100 million solar mass black holes, in a typical elliptical galaxy remnant with central stellar density 1,000 solar masses per cubic parsec, dynamical friction brings them from 100,000 light-years to 1,000 light-years separation in approximately 100 million to 500 million years. During this phase, the black holes are embedded in the galaxy's dense stellar core, interacting with billions of stars. As separation decreases below 1,000 light-years, the black holes begin forming a true binary, a gravitationally bound pair orbiting their common center of mass. Orbital mechanics now dominate their motion. For two equal-mass black holes of 100 million solar masses, separated by 100 light-years, the orbital period is approximately 1 million years, with orbital velocities around 100 kilometers per second. As they spiral inward through continued dynamical friction, periods shorten and velocities increase. At 10 light-years separation, the period drops to 10,000 years and velocities reach 1,000 kilometers per second. This is still far below the speed of light, so Newtonian orbital mechanics accurately describe motion. General relativistic effects remain small corrections, though they become increasingly important as separation shrinks. Dynamical friction weakens at small separations due to lost cone depletion. Stars on orbits, passing within the binary's influence, scatter to higher energies through gravitational slingshot interactions, gaining energy from the binary and being ejected from the central region. This creates a lost cone, a depleted region in phase space where stars on orbits, bringing them close to the binary, have been scattered away. Initially, two-body relaxation, random gravitational encounters between stars, refills the lost cone by scattering new stars onto intersecting orbits. But as the binary hardens, orbital energy increases while separation decreases. The lost cone refilling rate can't keep pace with the rate at which the binary ejects stars. The central stellar density drops, reducing dynamical friction and causing the binaries in spiral to stall. This is the final parsec problem, a theoretical difficulty where binary black holes might stall at separations around 1 parsec, taking far longer than the age of the universe to merge. The final parsec problem's severity depends on galaxy properties. In spherical, non-rotating galaxies, loss cone depletion is severe and binaries might genuinely stall. But real galaxies are not perfectly spherical. Triaxial distortions, departures from spherical symmetry, cause stellar orbits to become chaotic, allowing stars to wander into the loss cone even without two-body relaxation. Simulations of binaries in triaxial galaxies find that chaotic refilling allows continued hardening, though at reduced rates. Rotation also helps rotating galaxies have more complex orbital families, some of which intersect the binary despite loss cone depletion. Additionally, gas dynamics can drive binary evolution. If significant gas is present, as in gas-rich galaxy mergers, torques from a circumbinary disk gas orbiting the binary beyond roughly twice the binary separation can extract angular momentum and drive in spiral efficiently, potentially bypassing the final parsec problem entirely. Observational evidence for binaries at small separations comes from dual-active galactic nuclei systems. SDSS J 1536 plus 0441, discovered in 2013, shows 2 bright nuclei separated by approximately 1,400 light-years with a relative velocity of 210 km per second, consistent with orbital motion of a 50 million solar mass binary. Spectroscopy reveals double-peaked emission lines from ionized gas orbiting each black hole, confirming both are active. X-ray observations detect both nuclei with luminosities, indicating active accretion. The system provides a snapshot of a binary in the late dynamical friction phase, separated by thousands of light-years and spiraling inward. Similar dual AGN systems have been identified at separations from hundreds to tens of thousands of light-years, confirming that binaries do form and evolve towards smaller separations as theory predicts. OJ 287 represents a particularly well-studied binary candidate at very small separation. This quasar, located 3.5 billion light-years away, shows periodic brightness variations with a 12-year period. The favoured explanation involves a binary system with a 1/8 billion solar mass primary black hole and a 150 million solar mass secondary orbiting with a 12-year period. The secondary's orbit is eccentric, elongated rather than circular, and precesses due to general relativistic effects, rotating its orientation by about 39 degrees per orbit. Twice per 12-year orbit, when the secondary passes through pericenter, it plunges through the primary's accretion disk, creating shocks that heat the disk and produce brightness outbursts. The outbursts occurred in 1895, 1906, 1957, 1973, 1984, 1995, 2007, and 2019, matching theoretical predictions to within weeks. This precision supports the binary model and suggests orbital separation is only about 0.05 light-years far into the gravitational wave-driven regime. Eccentric orbits versus circular orbits significantly affect merger timescales and gravitational wave signatures. Circular binaries radiate gravitational waves steadily, causing smooth orbital decay. Eccentric binaries radiate most strongly at pericenter closest approach, where velocities are highest and space-time curvature is most extreme. This concentrated emission causes eccentricity to decrease over time. Orbits gradually circularize through gravitational wave radiation. However, If eccentricity is initially very high, as might occur in binary formation through dynamical capture in dense stellar environments, it can persist even into the final in-spiral. Eccentric mergers produce gravitational wave signals distinct from circular mergers, with bursts at each pericenter passage rather than smooth chirps. Detecting eccentric signals would provide evidence for specific formation channels and constrain binary evolution physics. As separation drops below 1 parsec, gravitational wave emission dominates binary evolution. The power radiated in gravitational waves is proportional to the square of the binary's quadrupole moment time derivative, how fast the mass distribution's asymmetry changes. For a binary of total mass m, with masses m1 and m2 separated by distance a, the radiated power is approximately 32/5 times g to the 4th over c to the 5th times mone times m2 squared times mone plus m2 divided by a to the 5th. This shows radiation increases dramatically as separation shrinks. Decreasing separation by a factor of 10 increases radiated power by a factor of 100,000. For 2,100 million solar mass black holes at 1 parsec separation, gravitational wave emission is negligible, taking over 1 billion years to significantly affect the orbit. At 0.01 parsecs, the timescale drops to 10 million years. At 0.001 parsecs, it's 10,000 years. The in-spiral accelerates exponentially as separation shrinks. The chirp mass determines gravitational wave signal strength and frequency evolution. Chirp mass is a combination of individual masses. M chirp equals m1 times m2 to the 3/5 power, divided by m1 plus m2 to the 1/5 power. For equal mass binaries, chirp mass equals approximately 0.43 times total mass. Chirp mass controls how quickly the gravitational wave frequency increases. During in-spiral, higher chirp mass means faster frequency evolution. Gravitational wave detectors measure chirp mass directly from the signal's frequency sweep, while individual masses require additional information like the signal's amplitude and phase. For supermassive black hole binaries, chirp masses range from millions to billions of solar masses, producing gravitational waves at nanohertz to millihertz frequencies, far below the 10 to 1000 Hz frequencies, accessible to ground-based detectors like LIGO. Gravitational waves rippling through spacetime. Gravitational waves are ripples in space-time itself, propagating at the speed of light and carrying energy away from accelerating masses. Albert Einstein predicted their existence in 1916 as a direct consequence of general relativity, but their detection required a century of technological development. On the 14th of September 2015, the Laser Interferometer Gravitational Wave Observatory LIGO detected gravitational waves for the first time, observing waves from 2 stellar mass black holes of 36 and 29 solar masses merging 1.3 billion light-years away. The detection, labeled GW150914, marked the beginning of gravitational wave astronomy. Since then, LIGO and its European counterpart Virgo have detected over 90 gravitational wave events, mostly from stellar mass black hole mergers, but also from neutron star collisions. These detectors operate at frequencies 10 to 1000 Hz, perfect for stellar mass systems, but completely insensitive to supermassive black hole mergers, which produce gravitational waves at much lower frequencies. Supermassive black hole binaries radiate gravitational waves at nanohertz frequencies, billionths of a hertz, corresponding to periods of months to years. A binary with total mass 200 million solar masses orbiting with a 1-year period produces gravitational waves at frequency 1 per year, or about 30 nanohertz. These waves are far too low for ground-based detectors, which are limited by seismic noise below 10 Hz. Detecting nanohertz gravitational waves requires entirely different techniques. Pulsar timing arrays use millisecond pulsars, rapidly rotating neutron stars, emitting radio pulses with extraordinary regularity as cosmic clocks. Gravitational waves passing between Earth and pulsars alternately compress and stretch the intervening space, causing pulse arrival times to vary by nanoseconds. By monitoring dozens of pulsars distributed across the sky for years to decades, arrays can detect the correlated timing variations caused by gravitational waves from supermassive black hole binaries across the universe. NanoGrav, the North American Nanohertz Observatory for Gravitational Waves, announced in June 2023 the detection of a gravitational wave background, a persistent, low-frequency hum created by the superposition of gravitational waves from thousands of supermassive black hole binaries throughout the pore cosmic volume. NanoGrav monitored 67 millisecond pulsars for 15 years using the Arecibo Observatory, Green Bank Telescope, and Very Large Array, measuring pulse arrival times with nanosecond precision. The data revealed correlated timing variations across pulsars consistent with gravitational waves at frequencies 1 to 100 nanohertz. The signal matches predictions for a population of supermassive black hole binaries with masses 100 million to 10 billion solar masses at various stages of inspiral. While not yet detecting individual binaries, the background detection confirms that supermassive black hole mergers occur throughout the universe at rates predicted by galaxy merger models. The European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Indian Pulsar Timing Array independently detected similar gravitational wave backgrounds in data released simultaneously with NanoGrav in 2023. The International Pulsar Timing Array combines data from all collaborations, providing the strongest evidence for the nanohertz gravitational wave background with statistical significance exceeding 4 sigma. The combined dataset includes over 100 pulsars monitored for up to 25 years, creating a galaxy-spanning gravitational wave detector with baselines thousands of light-years across. Future observations with more pulsars and longer timelines will transition from detecting the background to resolving individual loud binaries, the most massive systems approaching merger, which contribute significantly to the total signal. The strain amplitude H of gravitational waves measures how much space-time is stretched and compressed as the wave passes. For a binary with chirp mass m chirp at distance d radiating at frequency f, the characteristic strain is approximately h equals 2 times g to the 5/3 over c to the 4th times 2 pi f to the 2/3 times m chirp to the 5/3 divided by d. For a binary with chirp mass 100 million solar masses at 1 billion light-years, radiating at 10 nanohertz, the strain is roughly 10 to the minus 15th. This means space-time stretches and compresses by 1 part in a quadrillion, changing the distance between Earth and a pulsar 1,000 light-years away by about 100 meters. Detecting such tiny variations requires pulse timing, precision better than 100 nanoseconds over years to decades, achievable only with the most stable millisecond pulsars. Energy loss through gravitational wave radiation drives the binary inspiral. The rate of energy loss is dE over dt equals minus 32 over 5 times g to the 4th over c to the 5th times m1 squared times m2 squared times m1 plus m2 divided by a to the 5th. This energy comes from the binary's orbital energy, causing the orbit to shrink. As orbital separation A decreases, the energy loss rate increases rapidly proportional to A to the -5th power. This creates positive feedback. Energy loss causes orbits to shrink, which increases energy loss rate, which causes faster shrinking. The result is runaway and spiral that accelerates exponentially as merger approaches. For a 100 million solar mass equal mass binary starting at 1 parsec separation, gravitational wave emission dominates, driving the binary to merger in approximately 10 million years short on cosmic timescales. The chirp mass appears naturally in gravitational wave analysis because it determines the signal's time evolution. During in-spiral, gravitational wave frequency increases steadily as orbital separation decreases. The rate of frequency increase depends on chirp mass. dF over dt proportional to m chirp to the 5/3 times f to the 11/3. Higher chirp mass means faster frequency evolution of chirp. Ground-based detectors like LIGO observe frequency increasing from 10 Hz to over 100 Hz in fractions of a second for stellar mass mergers. Space-based detectors like LISA will observe supermassive binaries chirping from millihertz to 10 millihertz over weeks to months. Pulsar timing arrays observe the lowest frequencies where chirping is too slow to measure in human timescales, but the background amplitude encodes population chirp mass distribution. Different gravitational wave detector types access different frequency ranges and source populations. Ground-based interferometers like LIGO, Virgo, and CAGRA detect 10 to 1000 Hz. Ideal for stellar mass black holes of 5 to 100 solar masses and neutron stars, around 1.4 solar masses merging in the local universe within 1 to 10 billion light-years. Space-based interferometers, like LISA, will detect 0.1 MHz to 100 MHz, accessing intermediate mass black holes of 100 to 10,000 solar masses. Supermassive binaries of 100,000 to 10 million solar masses, and extreme mass ratio in spirals, where stellar mass objects spiral into supermassive holes. Pulsar timing arrays detect 1 nanohertz to 100 nanohertz. Observing the most massive supermassive binaries of 100 million to 10 billion solar masses across cosmic volumes. Together, these detectors provide complete coverage from nanohertz to kilohertz, spanning 9 orders of magnitude in frequency. GW190521, detected on the 21st of May 2019, represents a possible intermediate mass black hole merger. The signal showed 2 black holes of approximately 85 and 66 solar masses merging to produce a 142 solar mass remnant. The primary's mass of 85 solar masses lies in the pair instability gap, a mass range where stellar evolution theory predicts black holes shouldn't form because massive stars undergo pair instability supernovae, completely disrupting the star and leaving no remnant. The detection of an 85 solar mass black hole suggests either pair instability theory requires revision, or the black hole formed through mergers of smaller black holes in dense stellar environments like globular clusters. The remnant mass of 142 solar masses is the first confident detection of an intermediate mass black hole, bridging the gap between stellar mass and supermassive populations. Gravitational wave astronomy provides a fundamentally new way to observe the universe. Electromagnetic astronomy, optical, radio, X-ray, gamma ray depends on matter emitting or scattering light. Black holes emit no light. Neutron star interiors are opaque. The early universe before recombination was opaque to photons. Gravitational waves propagate freely through all matter, carrying information from the most extreme gravitational environments and the earliest cosmic epochs. Binary black hole mergers release most energy as gravitational waves, not light. GW 150914 radiated 5 billion solar masses, equivalent energy as gravitational waves, but produced no electromagnetic counterpart. Neutron star mergers release energy in both gravitational waves and electromagnetic emission, enabling multi-messenger observations that constrain neutron star equation of state and produce heavy elements like gold and platinum through rapid neutron capture nucleosynthesis. The final parsec problem slowing merger. The final parsec problem arises from loss cone depletion halting binary evolution at separations around 1 parsec. As a supermassive black hole binary hardens through stellar scattering, ejecting stars that pass close to the binary and thereby extracting orbital energy, it empties the region of phase space containing stellar orbits that approach closely. This loss cone becomes increasingly depleted as the binary evolves. In spherical, non-rotating stellar systems, two-body relaxation, random gravitational encounters, scattering stars onto new orbits is the only mechanism refilling the loss cone. For massive galaxies with velocity dispersions 200 to 300 km per second and central densities 100 to 1000 solar masses per cubic parsec, relaxation timescales exceed 10 to the 15th years, far longer than the universe's age. Without efficient loss cone refilling, the binary evolution stalls, potentially taking trillions of years to merge. This theoretical difficulty suggests that either galaxies have properties avoiding the problem or additional physics drives mergers. Solutions to the final parsec problem fall into 3 categories: stellar scattering in non-spherical systems, gas-driven migration, and triple black hole systems. Triaxial galaxy potentials, departures from spherical symmetry caused by bars, oval distortions, or ongoing mergers induce chaotic stellar orbits that naturally refill the loss cone without requiring two-body relaxation. Simulations of binaries in triaxial galaxies find that even modest triaxiality allows binaries to harden continuously, reaching gravitational wave-dominated regimes within 10 million to 100 million years cosmologically short timescales. Since most massive elliptical galaxies show some triaxiality, this mechanism might resolve the final parsec problem for most systems. However, whether galaxies remain sufficiently triaxial throughout binary evolution remains debated. Violent relaxation during merger might sphericalize galaxies before binaries fully harden. Gas torques from circumbinary disks provide a second solution. If significant gas is present, as in gas-rich major mergers, gas orbiting beyond roughly twice the binary separation forms a circumbinary disk with a central cavity cleared by the binary's tidal torques. Gravitational interactions between the binary and disk transfer angular momentum from binary to disk, extracting energy from the binary and causing it to shrink. Type 2 planetary migration, the process by which gas giant planets migrate through protoplanetary disks, operates identically for supermassive black hole binaries. Migration timescales depend on disk mass and viscosity. For a disk containing 1% of the binary mass, with standard viscosity parameter alpha equals 0.1, a 100 million solar mass binary can migrate from parsec to subparsec separations in 1 to 10 million years. Since gas-rich mergers contain 10 to the 10th solar masses of gas funneled towards centers, disk-driven migration seems viable for this merger type. Triple black hole systems offer a third mechanism. If a galaxy hosting a binary merges with a third galaxy before the binary coalesces, the system temporarily contains 3 supermassive black holes. The third black hole interacts gravitationally with the binary, extracting energy through 3-body encounters and potentially driving the binary to smaller separations. Additionally, the third hole might be directly ejected through a gravitational slingshot, carrying away orbital energy. Some simulations find that triples accelerate binary mergers by factors of 10 to 100 compared to binaries in isolation. However, triple formation requires specific merger histories, multiple major mergers occurring within timescales shorter than binary merger times. Observational evidence for triple systems is limited. A few candidates show 3 distinct nuclei in disturbed galaxies, but confirming all 3 are supermassive black holes rather than star clusters requires spatially resolving emission with X-ray or radio interferometry. OJ 287 exemplifies a system that apparently overcame the final parsec problem. With a 12-year orbital period and estimated separation around 0.05 light-years based on orbital mechanics, the binary has clearly reached separations well inside 1 parsec. The system's current evolution is dominated by gravitational wave emission. The 12-year period is shortening by approximately 40 seconds per orbit as the binary radiates energy. Extrapolating backward, the binary crossed 1 parsec separation roughly 1 million years ago, implying it traversed the final parsec in cosmologically short time. Whether gas, triaxiality, or some other mechanism drove the evolution isn't clear from observations, but the system's existence proves that final parsec crossing is possible. The binary will merge in approximately 10,000 to 100,000 years extremely soon on cosmic timescales. Offset active galactic nuclei provide observational evidence for sub-parsec binaries. When 2 black holes at sub-parsec separation both actively accrete gas, they appear as dual AGN2, compact emission regions spatially resolved in high-resolution imaging. SDSS-J 1536 plus 0441 shows 2 X-ray sources separated by 1,400 light-years, confirmed through Chandra observations with 0.5 arcsecond resolution. NGC 6240 shows 2 sources separated by 3,000 light-years, resolved by Chandra. Some systems show single AGN spatially offset from galaxy center by hundreds to thousands of light-years, interpreted as either recoiling black holes kicked by asymmetric gravitational wave emission, or binary systems where only 1 black hole is currently active. Distinguishing between these scenarios requires measuring velocities through Doppler shifts or detecting orbital motion through multi-epoch observations. Confirmed sub-parsec binaries remain rare despite theoretical predictions that they should be common. This observational deficit might reflect genuine physical scarcity. Perhaps most binaries genuinely stall at parsec scales or observational difficulties. Resolving sub-parsec separations at distances of tens to hundreds of millions of light-years requires angular resolution below 0.01 arcseconds, achievable only with space-based X-ray observatories like Chandra operating at their resolution limits or very long baseline radio interferometry. Additionally, identifying binaries requires that both black holes are active, but if gas accretion is intermittent, only 1 black hole might be detectable at any given time. Future facilities, like the Next Generation Very Large Array, with 10 times better resolution than current VLA, and the LINX X-ray Observatory concept, with arcsecond imaging at higher energies, will detect sub-parsec binaries more readily if they exist. Simulations testing final parsec solutions use N-body codes evolving millions of particles representing stars, dark matter, and gas. The direct N-body codes, like RSET's N-body series and the StarLab package, calculate gravitational forces between all particles exactly, allowing precise tracking of stellar scattering and loss cone refilling. These codes are computationally expensive, limiting simulations to 1 million particles and runtimes of weeks to months on supercomputers. Tree codes and particle mesh codes approximate forces to reduce computation, enabling simulations with 100 million to 1 billion particles, but sacrificing accuracy in dense central regions where the binary resides. Smoothed particle hydrodynamics codes model gas dynamics, simulating disk torques and gas-driven migration. Recent simulations combining high-resolution N-body and hydrodynamics find that realistic galaxies with triaxiality in gas drive binaries to gravitational wave-dominated regimes within merger timescales, suggesting the final parsec problem might not be a problem in nature, only in idealized spherical collisionless models. Accretion disks feeding the black holes. Accretion disks transform gravitational potential energy into radiation with efficiency far exceeding nuclear fusion. When gas falls toward a black hole, it doesn't fall directly inward, but settles into a rotating disk due to angular momentum conservation gas, orbiting the black hole at various distances, with inner regions moving faster than outer regions. Friction between adjacent regions with different velocities heats the gas through viscosity, converting orbital kinetic energy to thermal energy. This heat radiates away as electromagnetic radiation ranging from radio to X-rays, depending on temperature. The standard thin disk model, developed by Nikolai Shakura and Rashid Sunyaev in 1973, predicts disk structure and emission for black holes accreting below the Eddington limit. For supermassive black holes, disk temperatures reach 100,000 to 10 million Kelvin, producing optical, ultraviolet, and X-ray emission. The efficiency fraction of rest mass energy converted to radiation is approximately 10%, meaning a 100 million solar mass black hole accreting 1 solar mass per year releases energy equivalent to 10 million billion suns. Temperature profiles in accretion disks decline with distance from the black hole. The disk temperature at radius r is proportional to r to the minus 3/4 power and depends on black hole mass m and accretion rate. For a 100 million solar mass black hole accreting at 10% of Eddington rate, about 2 solar masses per year, the temperature at the innermost stable circular orbit, located at 3 Schwarzschild radii, or about 900 million kilometers, reaches roughly 1 million Kelvin. At 100 Schwarzschild radii, 30 billion kilometers temperature drops to 30,000 Kelvin. The inner hot regions emit X-rays and ultraviolet light. Outer cooler regions emit optical and infrared. Multi-wavelength observations detect emission across this range, confirming the disk structure predicted theoretically. Reverberation mapping measuring time delays between brightness variations at different wavelengths directly measures disk size, confirming predictions from standard thin disk models. The Eddington limit sets a natural maximum accretion rate determined by balancing gravitational infall against radiation pressure. Radiation from the disk exerts outward pressure on infalling gas through scattering off electrons. When radiation pressure equals gravitational force, accretion halts. The Eddington luminosity is L-ed equals 4 pi g mm proton c divided by sigma t, where sigma t is the Thomson's scattering cross-section. Numerically, L-ed approximately equals 1.3 times 10 to the 38th times m divided by solar mass ergs per second. For a 100 minus million solar mass black hole, L-ed equals 1.3 times 10 to the 46th ergs per second, or about 300 trillion solar luminosities. The corresponding Eddington accretion rate, assuming 10% efficiency, is roughly 2 solar masses per year. Quasars often accrete at 10 to 100% of Eddington rate, maximizing growth. Quiescent black holes, like Sgr A-star, accrete at 10 to the minus 6th Eddington rate, essentially starving. Super Eddington accretion can occur in specific circumstances. If accretion rate exceeds Eddington, radiation pressure should halt in full. But in thick disks or slim disks, where radiation is partially trapped by dense inflowing gas, photons diffuse slowly outward while gas continues falling in, allowing super Eddington rates. Some tidal disruption events, stars ripped apart by black hole tides, produce super Eddington accretion lasting weeks to months until the stellar debris disperses. Ultraluminous X-ray sources in nearby galaxies show apparent luminosities exceeding Eddington limits for stellar mass black holes. Interpreted as either intermediate mass black holes accreting sub-Eddington or stellar mass holes accreting super Eddington with anisotropic emission beamed toward observers. Super Eddington accretion might explain how supermassive black holes grew so massive so quickly in the early universe, reaching billion solar mass sizes when the universe was less than 1 billion years old. Circumbinary disks form when both black holes are embedded in gas during binary inspiral. The binary's tidal torques clear a central cavity extending to roughly twice the binary separation, creating an inner edge to the surrounding disk. Gas orbiting beyond this radius forms the circumbinary disk. Gravitational torques from the eccentric binary's time-varying potential transfer angular momentum to the disk, causing gas to spiral outward from the inner edge, while the binary extracts angular momentum and spirals inward. The central cavity isn't completely empty. Gas streams from the circumbinary disk can cross the gap, forming mini-disks around each individual black hole. These mini-disks accrete onto their respective black holes, powering individual AGN emission. The mini-disks are periodically refilled as streams cross the gap, potentially causing periodic brightness variations observable as periodic quasars. Periodic accretion variability provides a potential signature of binaries. As the binary orbits, its gravitational potential modulates gas flow from the circumbinary disk into mini-disks. If orbital timescale is years to decades accessible to monitoring campaigns, periodic brightness variations reveal the binary's presence. PG 1000, 302 minus 102. A quasar at redshift Z equals 0.278, corresponding to 3.5 billion light-years, shows sinusoidal brightness variations with a 5.2-year period detected in decade-long monitoring. The amplitude is about 0.14 magnitudes, or 14% brightness change. Interpretation as a binary with 4 times 10 to the 8th solar mass, total mass, and separation roughly 0.01 parsecs, predicts the binary will merge in approximately 100,000 to 1 million years cosmologically. Imminent. However, alternative explanations like precessing jets or warped disks can also produce periodicities. So confirming the binary nature requires additional evidence like Doppler-shifted emission lines from gas orbiting each black hole. Swift J 1000 644 plus 57, discovered on the 28th of March 2011, represents a tidal disruption event, a star destroyed by black hole tides. The event occurred in a galaxy 3.9 billion light-years away. A star passing within roughly 100 Schwarzschild radii of a supermassive black hole experiences tidal forces exceeding its self-gravity and is ripped apart. Roughly half the stellar debris falls toward the black hole on highly eccentric orbits, producing a luminous accretion flare lasting months to years as debris circularizes and forms an accretion disk. Swift J1000 644 plus 57 produced relativistic jets beamed toward Earth, amplifying observed brightness to 10 to the 48th ergs per second in gamma rays far exceeding Eddington luminosity. The event lasted over a year, gradually fading as debris was consumed. Tidal disruption events occur roughly once per 10,000 to 100,000 years per galaxy, providing rare glimpses of normally quiescent black holes suddenly flaring as they consume stars. Accretion disk viscosity, parameterized by the alpha viscosity prescription introduced by Sgr and Sunyaev, determines how efficiently angular momentum transports outward through the disk. The viscosity is written as proportional to alpha times pressure times scale height, where alpha is a dimensionless parameter, typically 0.01 to 0.1. Viscosity arises from turbulence driven by the magnetorotational instability, a magnetohydrodynamic instability discovered by Stephen Balbus and John Hawley in 1991, where weak magnetic fields threading the disk become unstable, growing exponentially and generating turbulence. Magnetohydrodynamic simulations resolving turbulence find effective alpha values 0.01 to 0.1, consistent with observational constraints from disk luminosities and sizes. Higher alpha means faster accretion and shorter disk evolution timescales. For binary systems, alpha affects disk-driven migration rates. Higher viscosity disks transport angular momentum more efficiently, accelerating binary in spiral. Comparing accretion physics in binary systems versus single black holes reveals important differences. Single black holes accrete from large-scale gas flows funneled inward by galaxy gravitational potential, forming standard thin disks extending to hundreds to thousands of Schwarzschild radii. Binaries clear central cavities, truncating the disk at the binary's tidal radius. Mini-disks around each black hole are fed by streams from the circumbinary disk rather than large-scale inflow, making accretion variable and time-dependent. The binary's precession, slow rotation of orbital orientation due to general relativistic effects, causes mini-disks to precess, potentially producing helical jets and time-variable emission. Observationally, these differences manifest as lower overall accretion rates in binaries due to cavity clearing, periodic variability from orbital modulation, and complex jet morphologies from precession signatures that help identify binary candidates among active galactic nuclei populations. Electromagnetic precursors to merger. Electromagnetic emission from supermassive black hole binaries provides advance warning of impending mergers, potentially alerting gravitational wave observatories to prepare for detection. Periodic quasar brightness variations caused by orbital modulation of accretion or relativistic beaming as jets precess offer one class of precursors. Doppler boosting from material orbiting the binary at relativistic speeds produces brightness variations at twice the orbital period as material alternately approaches and recedes from observers. Helical jet structures created by precessing accretion disks aligned with individual black hole spins rather than the binary orbital plane produce radio morphologies distinct from straight jets in single black holes. X-ray flares from disk-disk collisions, as mini-disks around each black hole gravitationally perturb each other, provide intermittent brightening. Predicted radio chirps gradual frequency evolution of periodic signals, as binaries in spiral should appear 10 to 100 days before merger for systems monitored at radio wavelengths. PG 1302-102's 5.2-year periodicity. Discovered through optical monitoring spanning 20 years by the Catalina Real-Time Transient Survey and confirmed by follow-up observations, stands as the strongest periodic quasar candidate. The sinusoidal brightness variation shows remarkable regularity, fitting a simple sine wave with root mean square residuals only 0.02 magnitudes, indicating genuine periodicity rather than stochastic variability. The period corresponds to orbital separation approximately 0.007 parsecs, or 1,400 astronomical units, for a binary with total mass 4 times 10 to the 8th solar masses inferred from quasar properties. At this separation, gravitational wave emission dominates orbital evolution, predicting merger within 100,000 to 1 million years. If the binary survives to merger, space-based detectors like LISA will detect gravitational waves months to years before coalescence, providing multi-messenger observations combining electromagnetic monitoring with gravitational wave astronomy. Doppler boosting amplifies emission from relativistic material, moving toward observers, while dimming receding material. For jets launched at speeds approaching light speed, the boosting factor is approximately 1 plus beta cosine theta to the third power, where beta equals velocity divided by light speed, and theta is the angle between jet direction and line of sight. When a binary's orbital motion adds velocities comparable to jet speeds, the beaming factor varies periodically, producing brightness variations. A binary with 100 million solar mass components at 0.01 parsecs, separation orbits at roughly 3,000 kilometers per second, or 1% light speed. If jets move at 90% light speed, orbital motion modulates beaming by factors of 1.5 to 2, producing 50 to 100% brightness variations at twice orbital period, observationally accessible for periods years to decades. Helical jet structures provide morphological evidence for binary-driven precession. The radio galaxy 3C75, located in the galaxy cluster Abell 400 at 300 million light-years, shows twin radio jets from 2 active galactic nuclei separated by 25,000 light-years. The jets are bent into shapes by the galaxy's motion through the intracluster medium at 1,200 kilometers per second, combined with orbital motion if the nuclei form a bound binary. Each jet extends 100,000 light-years before bending. The combination of orbital motion, galaxy motion through the cluster, and jet precession creates complex morphologies revealing dynamics. Whether 3C75 is a bound binary or a chance projection of 2 unrelated AGN remains debated. Measuring radial velocities through spectroscopy would distinguish bound orbital motion from line-of-sight projection. X-shaped radio galaxies display 4 jets extending from the core in an X configuration, interpreted as signatures of binary black hole mergers or rapid jet reorientation. The standard double-lobe morphology results from jets launched in opposite directions along the black hole spin axis, inflating lobes of radio-emitting plasma. X-shaped morphologies arise if jet direction changes by roughly 90 degrees, creating new lobes while old lobes fade. One formation scenario involves black hole spin flip during binary merger if pre-merger spins are misaligned with orbital angular momentum. Post-merger spin results from vector addition pointing in a new direction. Jets realigned with new spin axis create the second pair of lobes. Alternatively, rapid accretion flow realignment following merger could reorient jets without changing black hole spin. Over 100 X-shaped sources are catalogued, providing a population of merger remnants at various post-merger ages. Radio chirps represent predicted but not yet observed electromagnetic signatures of late-stage binaries. As binaries in spiral, orbital period decreases, orbits speed up as separation shrinks. Any periodic electromagnetic signal tied to orbital motion, such as brightness variations from accretion, variability, or beaming, will show periods shortening over time. For a binary radiating gravitational waves at 10 nanohertz with chirp mass 10 to the 9th solar masses, the frequency evolution rate is approximately 10 to the minus 16 hertz per second. Over 1 year of observations, the period would shorten by roughly 1 part in 100,000, marginally detectable with high-precision photometry or timing. In the final year before merger, as gravitational wave frequency sweeps through millihertz to 10 millihertz accessible to LISA, electromagnetic periods should shorten noticeably over months, providing smoking gun evidence for imminent merger. The Zwicky Transient Facility, an automated wide-field survey imaging the entire northern sky every few nights to detect transients and variables, is identifying periodic quasar candidates systematically. ZTF's multi-year baseline allows detecting periods from months to years. By 2023, ZTF identified over 100 candidates showing periodic optical variability, though most require confirmation through follow-up spectroscopy and multi-wavelength observations to distinguish binaries from other variability mechanisms like jet precession or accretion disk instabilities. The Vera C. Rubin Observatory, beginning operations in 2025, will detect thousands of periodic quasars through its 10-year legacy survey of space and time, imaging the entire southern sky every 3 to 4 nights. Cross-correlating optical periodic quasars with pulsar timing array, detections of gravitational wave backgrounds will statistically confirm that periodicities result from binaries. Predicted electromagnetic signatures in the final days before merger remain highly uncertain. As the binary reaches separations comparable to event horizon sizes tens to hundreds of Schwarzschild radii, relativistic effects dominate. Simulations using general relativistic magnetohydrodynamics evolve accretion flows and magnetic fields through the final orbits and merger. Results show complex time-dependent accretion patterns as mini-disks around each black hole are tidally disrupted and merge into a single disk around the remnant. Magnetic field lines connecting the black holes might snap and reconnect, releasing energy in flares. Jets might shut off temporarily as the accretion geometry reorganizes, then restart aligned with the remnant spin. These late-time processes occur over hours to days for 100 million solar mass binaries, producing potential optical and X-ray flares, detectable by survey telescopes monitoring the sky continuously. The moment of event horizon merger. The event horizons of 2 black holes merge when their separation drops below roughly 2 gm divided by c squared, where m is the total mass of the binary. For 100 million solar mass black holes, this critical separation is approximately 300 million kilometers, about twice the Earth-Sun distance. At this point, a common event horizon forms encompassing both black holes, creating a single, unified black hole. There is no physical surface collision. Event horizons are mathematical boundaries, marking the point of no return, where escape velocity equals light speed, not material surfaces. The horizons blend smoothly through a process described by general relativity's field equations. The merger is a purely gravitational phenomenon involving extreme warping of space-time geometry. As the black holes spiral inward through the final orbits, they reach velocities approaching 30% the speed of light, 90,000 kilometers per second, orbiting each other multiple times per second before plunging together. The final plunge begins when gravitational wave emission becomes so strong that orbits decay faster than orbital period. At separations around 6 to 10 Schwarzschild radii, roughly 1,800 to 3,000 million kilometers for 100 million solar mass black holes, the in-spiral transitions from a gradual, quasi-circular evolution to a rapid plunge lasting milliseconds. During the plunge, the black holes complete several final orbits with decreasing separation and increasing velocity. Numerical relativity simulations solving Einstein's equations on supercomputers show that orbital trajectories during this phase are complex, with significant deviations from simple Newtonian ellipses due to strong field general relativistic effects. Frame dragging, where each black hole's rotation drags space-time around it, causes orbital precession. Spin-orbit coupling, where black hole spins interact gravitationally with orbital angular momentum, further complicates dynamics. Ring-down follows the final plunge as the merged black hole settles into equilibrium. The newly formed black hole is initially distorted, spherical, with bumps and wiggles in the event horizon geometry. These distortions oscillate, radiating gravitational waves at specific frequencies called quasi-normal modes. Each mode corresponds to a particular oscillation pattern characterized by frequency and damping time. The fundamental mode dominates, with frequency approximately f equals 1 divided by 2 pi times square root of gm divided by c cubed divided by 1 plus z, where z is cosmological redshift. For a 200 million solar mass remnant, the result of merging two 100 million solar mass black holes, the fundamental mode frequency is roughly 100 MHz, perfectly suited for LISA detection. The damping timescale, how quickly oscillations die away, is approximately 1 millisecond, meaning ring-down completes within thousandths of a second. Quasi-normal modes are damped oscillations analogous to a struck bell ringing then fading. Unlike a bell with infinite modes extending to arbitrarily high frequencies, black holes have discrete quasi-normal mode spectra determined entirely by mass and spin through the no-hair theorem. The fundamental mode has the longest damping time and usually dominates the signal. Higher overtones oscillate faster and damp more quickly, contributing less energy to gravitational waves. Detecting multiple modes in ring-down signals allows testing the no-hair theorem, verifying that the remnant is indeed a black hole described by Kerr solution, with only mass and spin as free parameters. Deviations would indicate exotic compact objects like boson stars or gravastars, alternatives to black holes proposed in modified gravity theories. So far, all observed ring-down signals from stellar mass mergers are consistent with Kerr black holes. The final black hole mass is less than the sum of initial masses. Energy radiated as gravitational waves accounts for the missing mass through Einstein's E equals mc squared. For equal mass non-spinning mergers, approximately 5% of total mass converts to gravitational wave energy. For two 100 million solar mass black holes, this means 10 million solar masses equivalent to the mass of 10 million suns radiates away in seconds. Unequal mass ratios reduce radiated energy. The maximum efficiency occurs when masses are equal. Black hole spins significantly affect radiated energy. Aligned spins both black holes, spinning in the same direction. As orbital motion increase radiated energy to 7 to 8%. Anti-aligned spins reduce it to 2 to 3%. The remaining 92 to 98% of total mass becomes the remnant black hole mass. The remnant spin, characterized by the Kerr parameter, a spin angular momentum divided by mass, depends on initial spins and orbital angular momentum. For equal mass mergers with non-spinning black holes, orbital angular momentum converts entirely to remnant spin, yielding a approximately 0.69 moderately spinning. If both black holes have aligned, spins A equals 0.9 before merger, the remnant can have A up to 0.95, rapidly spinning and close to the theoretical maximum A equals 1. Extremely high spins, approaching 1, correspond to black holes rotating near the speed of light at their equators. Such rapidly spinning black holes are more efficient at extracting energy from accretion disks through the Blandford-Znajek mechanism, launching powerful jets. Measuring remnant spin through gravitational wave signals constrains merger parameters and predicts post-merger electromagnetic emission if gas is present. The no-hair theorem, proven mathematically by Stephen Hawking, Brandon Carter, and others in the 1970 seconds, states that black holes are characterized completely by three quantities: mass, spin, and electric charge. All other information about infalling matter, its composition, shape, internal structure, disappears beyond the event horizon, leaving no trace on the black hole's external gravitational or electromagnetic fields. For astrophysical black holes, electric charge is negligible. Any significant charge would attract oppositely charged particles from surroundings, neutralizing the whole. Thus, astrophysical black holes are fully described by mass m and dimensionless spin A. This remarkable simplicity makes black holes among the purest objects in physics. Despite forming from complex matter distributions, they settle into states described by just two numbers. Testing the no-hair theorem with gravitational wave observations requires detecting both in spiral and ring-down signals with high signal-to-noise ratio. The in-spiral waveform encodes the masses and spins of the individual pre-merger black holes. The ring-down encodes the mass and spin of the post-merger remnant. General relativity provides precise predictions for how initial parameters relate to final parameters. By measuring both and comparing, physicists test whether the remnant's properties match predictions assuming general relativity and the no-hair theorem. GW 150914. The first LIGO detection measured remnant mass 62 solar masses and spin A equals 0.68, consistent with predictions given initial masses 36 and 29 solar masses. Future detectors with better sensitivity will test the no-hair theorem at percent-level precision, searching for deviations indicating new physics beyond general relativity. The exact moment when a common horizon forms is subtle. As the black holes approach, their individual event horizons surfaces, marking points of no return, extend toward each other, deforming from spheres to ellipsoids due to tidal forces. When separation drops below a critical value, a mathematical surface appears connecting the horizons, forming a single, extended event horizon wrapping both black holes. This common horizon forms slightly before the black holes merge completely, when separation is still a few Schwarzschild radii. From this point onward, anything falling into the common horizon cannot escape, even if it falls into the region nominally between the two pre-merger horizons. The common horizons area always increases. Satisfying Hawking's area theorem, the black hole area never decreases in classical general relativity. The final horizon area exceeds the sum of initial areas, with the difference proportional to the energy radiated in gravitational waves. No electromagnetic signature necessarily accompanies event horizon merger if gas is absent. If both black holes are quiescent, not actively accreting, the merger is purely gravitational, producing gravitational waves but no light. The event horizons merge in vacuum. If gas is present, complex electromagnetic phenomena occur. Magnetic field lines threading each black hole's horizon might reconnect as horizons merge, releasing energy in flares. Accretion disks around each black hole tidally disrupt during the final orbits, creating shocks and hotspots. Gas falling into the rapidly evolving spacetime around merging holes experiences extreme gravitational forces, potentially producing X-ray and gamma-ray emission. Numerical simulations, including magnetohydrodynamics, predict electromagnetic luminosities ranging from 10 to the 42nd to 10 to the 46th ergs per second, comparable to bright supernovae to quasars lasting hours to days for. Supermassive mergers. Detecting such counterparts would provide smoking gun confirmation of merger and constrain gas content. Gravitational wave burst at coalescence. The gravitational wave luminosity peaks at merger, reaching approximately 10 to the 56th ergs per second for 2100 million solar mass black holes, equivalent to 10 to the 23rd solar luminosities. This is more power than all stars in the observable universe emit combined across all wavelengths. The peak lasts only milliseconds, but during that brief interval, the merging black holes are the brightest objects in the gravitational wave sky, outshining all other sources. The total energy radiated is 3 to 5% of the total mass for typical mergers, corresponding to 3 to 5 million solar masses for a 100 million solar mass equal mass binary. This energy propagates outward as gravitational waves, ripples in space-time geometry, traveling at the speed of light, stretching and compressing space perpendicular to their direction of propagation. Detectors billions of light years away can detect these waves, though the strain fractional change in distance is only 10 to the minus 15th to 10 to the minus 18th by the time waves reach Earth. The duration of strong gravitational wave emission spans hours to days for the inspiral phase, transitional to milliseconds for merger and ringdown. For 2100 million solar mass black holes starting from 1 parsec separation where gravitational wave emission dominates, the inspiral lasts approximately 10 million years. But most energy radiates during the final day when separation drops below 1000 Schwarzschild radii, about 300 billion kilometers. During this final day, gravitational wave frequency sweeps from microhertz to millihertz. The final hour sees frequency increasing from 0.1 millihertz to 1 millihertz. The final minute covers 1 to 10 millihertz. The final second reaches 10 to 100 millihertz, precisely the frequency range where LISA will be most sensitive. The merger itself, the plunge and ringdown, occupies only milliseconds, radiating the final burst at peak frequency around 100 MHz for 200 million solar mass remnants. LISA, the Laser Interferometer Space Antenna, is a planned, space-based gravitational wave observatory consisting of 3 spacecraft forming an equilateral triangle with 2.5 million kilometer sides, orbiting the Sun trailing Earth by about 50 million kilometers. Each spacecraft houses a free-floating test mass, a gold-platinum cube, and lasers precisely measure distances between test masses on different spacecraft. Gravitational waves passing through the constellation alternately stretch and compress the triangle's sides by femtometers, quadrillionths of a meter. LISA will detect gravitational waves at frequencies 0.1 MHz to 100 MHz, ideally suited for supermassive black hole mergers with total masses 100,000 to 10 million solar masses. The mission, jointly led by NASA and ESA, is scheduled to launch in the mid-2032 on an Ariane 6 rocket, with 3 spacecraft deployed sequentially into heliocentric orbits. Detection range for LISA extends to redshift Z, approximately 20, corresponding to look-back times exceeding 13 billion years when the universe was less than 500 million years old. A merger of 2 1 million solar mass black holes at redshift, 10 about 13.2 billion light-years distance, produces signals detectable with signal-to-noise ratio exceeding 100, allowing precise measurement of masses, spins, distance, and sky position. More massive mergers of 10 to 100 million solar masses are detectable to even greater distances, though such massive systems are rarer at high redshift. LISA will observe the merger history of supermassive black holes across cosmic time, revealing when and how these objects grew from smaller seeds to the billion solar mass giants observed in today's universe. Counting mergers at different redshifts constrains galaxy merger rates and black hole formation scenarios. The ring-down frequency provides a direct measurement of remnant mass. The fundamental quasi-normal mode frequency is f equals 0.32 divided by pi times c cubed divided by gm times 1 divided by 1 plus z. Solving for mass gives m equals 0.32 divided by pi f times 1 plus z times c cubed divided by g. Measuring frequency to 1% precision determines mass to 1% precision independent of any other information. This is a unique feature of ring-down in spiral signals, require measuring both masses and distance to extract individual parameters, involving degeneracies between parameters. Ring-down breaks these degeneracies, allowing mass and spin to be measured separately. Combining in spiral and ring-down measurements overdetermines the system, providing consistency checks and testing general relativity. Any inconsistency between in spiral derived and ring-down derived parameters would indicate deviations from general relativity or exotic phenomena. GW190521, detected on the 21st of May 2019, is a candidate intermediate mass black hole merger with total mass approximately 150 solar masses and remnant mass 142 solar masses. The signal duration in LIGO's sensitive band was only 0.1 seconds, far shorter than typical stellar mass mergers lasting seconds, because the merger frequency swept through LIGO's band rapidly for such high total mass. The short duration and high mass make parameter estimation uncertain, but best fit values suggest primary mass 85 solar masses, secondary 66 solar masses, remnant mass 142 solar masses, and distance 5.3 billion light-years. The system radiated approximately 8 solar masses in gravitational waves, about 5% of total mass, consistent with expectations. This detection hints at a population of intermediate mass black holes bridging stellar mass and supermassive populations, possibly formed through hierarchical mergers in dense stellar clusters. Energy radiated in gravitational waves escapes the system permanently, carrying away orbital angular momentum and causing orbits to shrink. The power radiated is proportional to the square of the mass quadrupole moment's second time derivative. For circular orbits, this is p equals 32 over 5 times g to the 4th over c to the 5th times m1 squared times m2 squared times m1 plus m2 divided by a to the 5th. The a to the -5th dependence means radiation increases extremely rapidly as separation decreases. Halving the separation increases radiated power by a factor of 32. This runaway emission is why binaries spend millions of years at parsec separations but merge in milliseconds once reaching Schwarzschild radius separations. The energy comes from orbital binding energy. As energy radiates away, orbits become more tightly bound, paradoxically releasing more energy and accelerating radiation. Gravitational wave strain measured by detectors depends on intrinsic source properties and distance. The strain amplitude is proportional to chirp mass to the 5/3 power times frequency to the 2/3 power divided by distance. This means more massive sources produce stronger signals proportional to m to the 5/3. Higher frequencies also increase strain, though with weaker dependence proportional to f to the 2/3. Most importantly, strain decreases linearly with distance doubling, distance halves strain. For LISA detecting a 1 million solar mass merger at 1 billion light-years, peak strain is approximately 10 to the -17th. At 10 billion light-years, strain drops to 10 to the -18th near LISA's sensitivity limit. Ground-based detectors like LIGO detect strains around 10 to the -21st from stellar mass mergers hundreds of millions of light-years away, requiring extraordinary instrument precision. The gravitational wave signal carries information about the binary's orientation, orbital eccentricity, and black hole spins encoded in waveform details. Inclination, the angle between orbital angular momentum and line of sight, affects signal amplitude. Face-on binaries with inclination near 0 or 180 degrees produce maximum strain, while edge-on binaries with inclination 90 degrees produce half the strain. Eccentricity produces harmonics in the frequency spectrum. Eccentric binaries emit at multiples of orbital frequency, not just twice as circular binaries do. Spin-orbit coupling causes orbital precession, modulating gravitational wave amplitude and phase in characteristic patterns. Spin-spin coupling between the two black hole spins creates additional modulations. Measuring these effects requires high signal-to-noise ratios, typically exceeding 30, accessible for nearby bright sources. Future detectors with improved sensitivity will measure spins and orientations precisely for most detected mergers. Localizing sources on the sky requires triangulation between multiple detectors. A single detector measures strain but cannot determine source direction. Gravitational waves from any direction produce similar signals. Two detectors, separated by thousands of kilometers, see signals arrive at slightly different times due to light travel time differences across the baseline. This timing delay constrains the source to a ring on the sky perpendicular to the baseline. Three detectors provide two independent baselines, narrowing localization to one or two patches on the sky. LIGO's two detectors in Hanford, Washington, and Livingston, Louisiana, separated by 3,000 kilometers, localize sources to regions hundreds to thousands of square degrees. Adding Virgo in Italy and Kagra in Japan improves localization to tens of square degrees. LISA's constellation geometry provides excellent localization sources at high signal-to-noise ratio are localized to arc minutes, enabling targeted electromagnetic follow-up. Gravitational recoil kicks from asymmetry. Anisotropic gravitational wave emission creates net momentum, kicking the merged black hole in the opposite direction through conservation of momentum. When gravitational waves radiate symmetrically in all directions, net momentum cancels radiation. In one direction is balanced by radiation in the opposite direction. But for black holes with unequal masses or misaligned spins, gravitational wave emission is asymmetric, carrying more momentum in some directions than others. The recoiling black hole receives a kick velocity that can reach thousands of kilometers per second, sufficient to eject it from even massive galaxies. Maximum kick velocities around 5,000 kilometers per second occur for specific configurations. Comparable masses with mass ratio around 0.7 to 0.85, and spins aligned in the orbital plane but anti-aligned with each other. These optimal kick configurations are relatively rare, but even modest kicks of 100 to 500 kilometers per second are common, displacing black holes from galactic centers by hundreds to thousands of light-years. The kick velocity depends on three contributions: mass asymmetry kicks, spin-orbit kicks, and spin-spin kicks. Mass asymmetry kicks result from unequal mass ratios. For a binary with mass ratio q equals m2 over m1, where m1 is larger, the kick velocity is roughly 150 kilometers per second times q squared times 1 minus q divided by 1 plus q squared. Maximum occurs at q approximately 0.7, giving kicks around 170 kilometers per second for non-spinning holes. Spin-orbit kicks arise when black hole spins are misaligned with orbital angular momentum, causing precession that creates asymmetric radiation. These can reach 500 to 1,000 kilometers per second. Spin-spin kicks result from interactions between the spins themselves, maximized when spins are comparable in magnitude, but aligned in the orbital plane and anti-aligned with each other. The combination of all three effects in optimal configurations produces the maximum possible kick around 5,000 kilometers per second. Escape velocity from galaxies determines whether kicks eject black holes permanently or merely displace them from centers. The Milky Way's escape velocity from the solar system's position, 26,000 light-years from center, is approximately 550 kilometers per second. At the galactic center, escape velocity is higher, around 1,000 kilometers per second. Dwarf galaxies have much lower escape velocities, 100 to 300 kilometers per second, making them vulnerable to black hole ejection even from modest kicks. Giant elliptical galaxies like M87 have escape velocities 1,500 to 2,000 kilometers per second at their centers, retaining all but the most extreme kicks. Statistical studies predict that roughly 10% of supermassive black hole mergers produce kicks exceeding 1,000 kilometers per second, and about 1% produce kicks exceeding 3,000 kilometers per second. The fraction ejected permanently depends on host galaxy mass. Most black holes in massive galaxies remain bound despite kicks. CID 42, discovered in Deep Chandra X-ray Observatory images of the Cosmos Survey Field, is a candidate recoiling supermassive black hole. Located at redshift Z equals 0.359, corresponding to distance 3.8 billion light-years, the X-ray source is spatially offset from the optical galaxy center by 5 kiloparsecs, about 8,000 light-years. Spectroscopy shows the X-ray source has velocity 1,300 kilometers per second relative to galaxy's systemic velocity, consistent with recoil from a recent merger. The black hole mass is estimated at 10 million solar masses based on X-ray luminosity. The offset and velocity are consistent with a kick approximately 1,500 kilometers per second from a merger roughly 5 million years ago. Alternative explanations include a dual AGN system viewed in projection, but the single narrow emission line spectrum favors the recoil interpretation. CID 42 demonstrates that kicks do occur in nature and can displace black holes measurably. SDSS J092712. 65 plus 294,344 shows an even more dramatic offset. This system, at redshift Z equals 0.714, corresponding to 6.4 billion light-years, has an active galactic nucleus offset from its elliptical host galaxy by 3.8 kiloparsecs, about 12,000 light-years. Spectroscopy reveals velocity offset 2,650 kilometers per second, among the highest measured for any offset AGN. The extreme velocity suggests a recent merger with kick close to the galaxy's escape velocity. The black hole might eventually escape if the kick exceeded escape velocity, or it might fall back to the galactic center over hundreds of millions of years if the kick was sub-escape. The large offset and high velocity make SDSS-J 927 plus 2,943 the best recoiling black hole candidate, though confirming the recoil scenario requires ruling out alternatives like binary systems or chance superposition. Hang-up kicks represent configurations minimizing recoil. When black hole spins align with orbital angular momentum and with each other, all angular momenta parallel gravitational wave emission is more symmetric, producing minimal kicks, typically below 100 kilometers per second. This aligned configuration also maximizes the final black hole spin, producing Kerr parameters A approaching 0.95. Conversely, anti-aligned spins opposite to orbital angular momentum produce larger kicks and lower final spins, around A equals 0.4. Whether spins preferentially align or anti-align depends on binary formation history and accretion dynamics. If both black holes accrete from a coherent gas supply, a common circumbinary disk torques might align spins with orbital angular momentum, favoring hang-up configurations and small kicks. If black holes formed from independent galaxies with uncorrelated orientations, spins might be randomly oriented, producing a broader kick distribution, including large kicks. Observational signatures of recoiling black holes include spatial offsets, velocity offsets, and disturbed morphologies. Offset AGN show X-ray or optical emission displaced from galaxy photometric centers by kiloparsecs. Velocity offsets appear in spectroscopy as Doppler-shifted emission lines from gas orbiting the displaced black hole. Disturbed morphologies, asymmetric shells, tidal features, or irregular isophotes indicate recent mergers that might have produced kicks. However, distinguishing recoiling black holes from dual AGN systems, wandering black holes accreted during minor mergers or projection effects is challenging. Multi-epoch observations tracking whether offsets change over time would definitively confirm recoil by measuring black hole motion. Current surveys have identified dozens of offset AGN candidates, but confirmed recoiling black holes number only a handful due to ambiguous alternative explanations. The demographics of recoiling black holes depend on merger rates, kick velocity distributions, and galaxy properties. Simulations combining black hole merger rates from galaxy formation models with kick velocity distributions from general relativity calculate recoil populations. Results predict that at any given time, roughly 1% of massive galaxies host recoiling black holes displaced more than 1 kiloparsec from centers. Lower mass galaxies and dwarf galaxies have higher displacement fractions due to lower escape velocities. Some kicked black holes escape host galaxies entirely, becoming intergalactic wanderers. These ejected holes continue traveling through intergalactic space, potentially accreting diffuse gas and producing low luminosity AGN detectable in deep X-ray surveys. The wandering population might comprise 5 to 10% of all supermassive black holes by mass, though direct observational constraints are lacking. Recoil kicks affect supermassive black hole mass functions and galaxy black hole correlations. Ejection removes black holes from galaxies, breaking the M-sigma relation for affected systems. Galaxies that lose their black holes through ejection will have lower black hole masses than M-sigma predicts, creating scatter in the relation. Over cosmic time, ejection removes the most massive black holes. Preferentially, high-mass mergers produce the strongest kicks. This truncates the high-mass end of the black hole mass function, explaining why black holes above 10 billion solar masses are rare despite expectations from merger-driven growth. However, observations find very tight M-sigma correlations, with scatter only 0, 3 decks, suggesting most galaxies retain their black holes. Either kick velocities are generally lower than maximum predictions, or galaxies experiencing large kicks are rare, or ejected black holes eventually return to galactic centers through dynamical friction with dark matter halos, reshaping the host galaxy structure. Supermassive black hole binaries gravitationally scatter stars during inspiral, ejecting stars from galactic centers and creating depleted cores. As the binary orbits, stars passing within roughly twice the binary separation undergo three-body interactions. The binary and star exchange energy and angular momentum. Most stars gain energy through gravitational slingshot, increasing their velocities and ejecting them to larger radii. The binary loses energy, causing its orbit to shrink. This is the stellar hardening mechanism that drives binary evolution in the loss cone. Over millions of years, this process ejects 10 to the 8th to 10 to the 9th solar masses of stars from the central kiloparsec, creating cores, low-density central regions observable in massive elliptical galaxies. The core radius scales with binary properties. Larger and more massive binaries create larger cores, typically 100 to 500 light-years in radius for giant ellipticals. M87, the supergiant elliptical galaxy containing the 6.5 billion solar mass black hole imaged by the Event Horizon Telescope, exhibits a prominent core with radius approximately 500 light-years. The missing mass stars that would be present if the density profile continued to the center is estimated at 2 billion solar masses. This mass deficit matches expectations for a binary that merged after hardening through stellar scattering. The deficit implies the binary underwent roughly 100 hardening timescales, each ejecting about 20 million solar masses. Combining this with dynamical friction timescales predicts the binary spent about 100 million to 1 billion years at separations 1 to 100 light-years before reaching gravitational wave-dominated regime. M87's core provides a fossil record of past binary evolution, demonstrating that binaries do traverse the final parsec through stellar scattering when galaxies are sufficiently triaxial or massive. Tidal disruption of star clusters occurs when clusters pass close to the binary. Globular clusters, dense stellar systems containing 100,000 to 1 million stars in regions 30 to 300 light-years across orbit throughout galaxies, including near centers. When a cluster passes within the binary's influence, tidal forces from the binary exceed the cluster's self-gravity, ripping it apart. Cluster stars scatter across the galaxy, contributing to the diffuse stellar population. The rate of cluster disruption increases dramatically during binary inspiral, when tidal forces are strongest. Observations of massive elliptical galaxies find fewer globular clusters in central kiloparsec regions compared to model predictions, consistent with tidal destruction by binaries. The The deficit suggests most giant ellipticals experienced binary evolution, even if binaries have since merged. Stellar collisions increase in rate during binary and spiral due to increased stellar density in the central region and gravitational focusing by the binary. In isolated galaxies, stellar collision rates are negligible, roughly 10 to the minus 12th per star per year in galactic center conditions. But near a hardening binary, stellar density increases as stars are scattered onto orbits, bringing them repeatedly close to the binary. The binary's gravitational focusing deflects stellar trajectories, increasing collision cross-sections. Combined effects increase collision rates by factors of 100 to 1000 inches the central parsec during binary evolution. A binary evolving over 10 million to 100 million years in the central parsec might produce 100 to 1000 collisions, creating a population of collision products, merged stars with unusual properties. Blue stragglers are stars appearing younger than globular cluster ages, explained as merger products. In old globular clusters with ages 10 to 13 billion years, the most massive stars still on the main sequence are about 0.8 solar masses, red, cool stars. But blue stragglers are hotter and more massive, typically 1.2 to 1.5 solar masses, suggesting ages only 3 to 5 billion years. They formed either through stellar collisions, merging two 0.7 solar mass stars into a 1.4 solar mass star that appears younger, or through mass transfer in binary systems. Stellar collisions, driven by black hole binaries, provide a formation channel. Detecting blue stragglers near galactic centers would provide indirect evidence for past binary evolution, though distinguishing collision products from young stars formed recently in starbursts is challenging. N-body simulations model stellar dynamics and binary evolution by integrating equations of motion for millions of particles representing stars. The NBODY series of codes, developed by Sgr A-star starting in the 1960 seconds and continuously improved, use sophisticated algorithms like Ahmad-Cohen neighbor schemes and KS regularization to handle close encounters accurately. These codes directly integrate Newton's equations without approximations, providing exact dynamical evolution within numerical precision limits. Modern supercomputer runs with 10 million particles, evolve systems for timescales 10 million to 100 million years, capturing binary hardening, core formation, and stellar scattering. Results confirm theoretical predictions. Binaries create cores with mass deficits matching binary binding energy. Binaries harden through stellar scattering on timescales 100 million to 1 billion years in massive galaxies. And triaxiality accelerates evolution by refilling the loss cone. Comparison between simulations and observations reveals that most massive elliptical galaxies have cores consistent with binary evolution. Surveys using Hubble Space Telescope imaging measured surface brightness profiles for hundreds of ellipticals, finding roughly 80% show depleted cores, while 20% show power law profiles extending to centers. The core fraction increases with galaxy mass. Nearly all giant ellipticals with masses exceeding 10 to the 11th solar masses have cores. Lower mass ellipticals and spirals typically lack cores, consistent with lower merger rates, and less massive black holes producing smaller cores difficult to resolve. The statistical connection between cores and galaxy mass supports merger-driven evolution. More massive galaxies experience more mergers, producing more binaries, creating more cores. Gravitational slingshot operates on stars, star clusters, dark matter particles, and even smaller black holes passing near binaries. The energy gain from a single encounter with a binary scales as the square of the binary's orbital velocity. For a 100 million solar mass binary at 1 light-year separation, orbital velocity is roughly 300 kilometers per second. Stars passing within 1 light-year gain velocities, typically 100 to 500 kilometers per second, sufficient to eject stars from galactic centers to outer halos. Some stars gain velocities exceeding galactic escape velocity, becoming hypervelocity stars, traveling through intergalactic space. The Hill's mechanism binary supermassive black hole ejection is one proposed origin for observed hypervelocity stars, though interactions with single supermassive black holes can also produce them. Several dozen hypervelocity star candidates have been identified with velocities 300 to 1,000 kilometers per second, supporting the binary ejection scenario, triggering starbursts and quenching. Galaxy mergers compress gas through shockwaves, triggering intense star formation called starbursts. When two galaxies collide, they're giant molecular clouds, gas clouds, containing 100,000 to 10 million solar masses, each collide at velocities hundreds of kilometers per second. The collisions create shockwaves that compress gas, increasing density by factors of 10 to 100. Compressed gas cools rapidly through molecular line emission, fragmenting into dense cores that gravitationally collapse to form stars. Star formation rates in starburst galaxies reach 100 to 1,000 solar masses per year, compared to 1 to 2 solar masses per year in quiescent spirals like the Milky Way. Starbursts last 100 million to 1 billion years, the time required to consume available gas or for feedback processes to halt star formation. During this period, 10 to the 10th to 10 to the 11th, solar masses of stars form, comparable to the entire stellar mass of the Milky Way. The starburst phase coincides with active galactic nucleus activity, as gas funneled toward the center feeds both star formation and black hole accretion simultaneously. Observations find that merger-driven starbursts and AGN are strongly correlated. Roughly 70% of luminous infrared galaxies hosting starbursts also show AGN signatures in X-ray or mid-infrared emission. The physical connection is straightforward. Gravitational torques during merger remove angular momentum from gas, causing it to spiral inward. Gas reaches the central killer parsec, where it forms stars prolifically, while simultaneously accreting onto the central supermassive black hole, powering quasar activity. This coevolution explains the observed M-sigma relation black holes and galaxy bulges grow together during mergers through regulated feedback, where AGN energy injection prevents unlimited growth. AGN feedback removes gas from galaxies through powerful winds driven by radiation pressure and jets. When a supermassive black hole accretes near the Eddington rate, the accretion disk's radiation exerts significant pressure on surrounding gas. Momentum transfer from absorbed photons accelerates gas to velocities 1,000 to 10,000 kilometers per second, exceeding galactic escape velocities. These AGN-driven winds sweep through the galaxy, entraining star-forming gas and expelling it into the intergalactic medium. Observations using optical spectroscopy detect these winds as blue-shifted absorption lines from gas flowing toward observers. X-ray spectroscopy reveals highly ionized winds with velocities up to 30,000 kilometers per second in nearby AGN. The mass outflow rates inferred from observations reach 100 to 1,000 solar masses per year, comparable to or exceeding star formation rates, demonstrating that AGN feedback can indeed quench star formation. The mechanical luminosity of AGN winds the kinetic energy carried by outflowing gas per unit time is approximately 5% of the AGN's bolometric luminosity for typical systems. For a quasar with luminosity 10 to the 46th ergs per second, the mechanical luminosity is 5 times 10 to the 44th ergs per second. This energy heats and accelerates gas throughout the galaxy. When deposited in star-forming regions, it raises gas temperatures above the threshold for gravitational collapse, preventing new star formation. The energy also unbinds gas from the galactic potential, ejecting it permanently. Cosmological simulations, including AGN feedback, successfully reproduce observed galaxy luminosity functions and color distributions without feedback. Simulations overproduce massive galaxies as gas cools and forms stars too efficiently. With feedback calibrated to observed AGN properties, simulations match observations, confirming AGN feedback's critical role in galaxy evolution. Quenching transforms star-forming blue galaxies into passive red galaxies devoid of ongoing star formation. Blue galaxies contain young, hot stars emitting optical and ultraviolet light, with ongoing star formation at rates maintaining stellar populations. Red galaxies contain old, cool stars emitting primarily in red and infrared, with negligible star formation. The transition from blue to red requires removing or heating gas to halt star formation. AGN feedback, driven by black hole growth during mergers, provides the mechanism. As the black hole grows massive enough, feedback, energy output, exceeds the binding energy of galactic gas, ejecting or heating it irreversibly. Star formation ceases within 100 million to 1 billion years as existing gas is consumed or expelled. The galaxy fades from blue to red as short-lived blue stars die and aren't replaced, leaving only long-lived red stars. M82, the prototype starburst galaxy, located 12 million light-years away in the constellation Ursa Major, exhibits star formation rate approximately 10 solar masses per year, 10 times the Milky Way's rate. Hubble and Chandra observations reveal hundreds of young star clusters with ages 1 to 10 million years, supernovae exploding at rates exceeding 1 per decade, and superwinds galactic-scale outflows driven by combined energy from supernovae and stellar winds, extending 10,000 light-years above and below the galactic disk at velocities 500 to 1,000 kilometers per second. M82 was disturbed by a close encounter with the nearby spiral M81 roughly 300 million years ago. Tidal forces from the encounter compressed M82's gas, triggering the starburst. M82's AGN is relatively weak, suggesting black hole growth lags behind starburst in this system. Feedback hasn't yet quenched star formation. The duration of starburst and AGN phases depends on gas supply and feedback strength. Gas-rich major mergers contain 10 to the 10th solar masses of gas funneled to central kiloparsecs. If star formation consumes gas at 100 solar masses per year, the gas exhaustion timescale is 100 million years. If AGN feedback removes gas at 500 solar masses per year, quenching occurs in 20 million years. Observations show AGN luminosities peak roughly 100 million to 300 million years after merger, then decline rapidly as gas is depleted or expelled. Starbursts peak earlier, within 50 to 100 million years, because gas in outer regions forms stars before reaching the black hole. The time delay between starburst and AGN peak supports the merger-driven coevolution scenario and explains why most luminous quasars reside in galaxies with post-starburst stellar populations. Starbursts ended recently, while AGN continues consuming remaining gas, jet launching and reorientation. Jets collimated outflows of relativistic plasma extending thousands to millions of light-years from black holes are launched through the Blandford-Znajec mechanism, extracting energy from spinning black holes. When a black hole rotates, it drags space-time around it through frame-dragging effects described by the Kerr metric. Magnetic field lines threading the event horizon are anchored to distant regions and twist as the black hole rotates. This twisting extracts rotational energy from the black hole, converting it to electromagnetic energy that accelerates particles along field lines to relativistic speeds. The jet power depends on black hole spin A and magnetic field strength B threading the horizon. P jet approximately equals 10 to the 44th times A squared times B squared times M squared ergs per second, where B is in Gauss and M is in solar masses. For a rapidly spinning 100 minus million solar mass black hole with B equals 1000 Gauss, typical for accretion disk, magnetic field's jet power reaches 10 to the 47th ergs per second, comparable to luminous quasars. Jets align with black hole spin axes because magnetic field geometry near the horizon is controlled by spin. Frame dragging creates an ergosphere, a region outside the event horizon, where space-time rotation drags everything into rotation with the black hole. Magnetic field lines in the ergosphere twist into helical structures aligned with the spin axis. Particles accelerate along these twisted field lines, producing jets perpendicular to the accretion disk and parallel to the spin axis. If the black hole's spin axis is misaligned with the binary's orbital angular momentum during inspiral, jets precess as orbital torques cause spin precession. When the binary merges, the remnant black hole's spin points in a direction determined by vector addition of the two pre-merger spins and orbital angular momentum. If this new spin direction differs significantly from pre-merger directions, jets realign to the new axis, potentially changing direction by 90 degrees or more within thousands of years. X-shaped radio galaxies display 4 lobes extending from the nucleus in an X configuration, interpreted as evidence for jet reorientation following black hole mergers. The standard double-lobed morphology has jets extending in opposite directions, inflating lobes of radio-emitting plasma at the jet termination points. X-shaped sources have 2 additional lobes oriented roughly perpendicular to the main lobes. Formation scenarios include spin flip during binary merger jets, initially align with one spin axis, then realign to the remnant spin axis after merger, creating the second pair of lobes while the first pair fades. Another scenario involves rapid accretion flow, realignment following merger, reorienting the inner accretion disk and jets without changing black hole spin. Over 100 X-shaped radio galaxies are catalogued, with sizes ranging from 100 kiloparsecs to several megaparsecs. Their existence provides indirect evidence for binary mergers, even if binaries merged millions of years ago. 4, C plus 0, 0, 58, an X-shaped radio galaxy at redshift, Z equals 0.27, corresponding to 3 billion light-years, shows particularly clear morphology, with 4 lobes extending symmetrically. The primary lobes span 400 kiloparsecs, with spectral ages inferred from synchrotron emission and spectral steepening, approximately 10 million years. The secondary lobes span 200 kiloparsecs, with spectral ages approximately 5 million years, consistent with formation after the primary lobes. The active nucleus currently produces jets aligned with the secondary lobes, indicating the active jet direction is the new orientation. If the reorientation resulted from a binary merger, the merger occurred roughly 5 to 10 million years ago, recent on cosmic timescales. Radio polarization observations show magnetic field orientations differing between primary and secondary lobes, supporting the reorientation scenario over alternative models like backflow or buoyancy-driven morphologies. Jet precession during binary and spiral creates helical jet morphologies as jets wobble over orbital timescales. If the binary orbital period is years to decades and the jets are relativistic, the jet appears as a helical structure on scales light-years to hundreds of light-years from the nucleus. Very long baseline interferometry radio imaging with sub-milliarc second resolution can resolve these structures in nearby AGN. Several sources show evidence for helical jets or bent jet bases, though distinguishing precession from intrinsic jet instabilities like Kelvin-Helmholtz modes is challenging. Precession timescales depend on orbital period and spin-orbit coupling strength. For a binary with 12-year orbital period, like OJ 287, jets should precess with similar period, creating detectable morphological variations over decade-long monitoring campaigns. Cygnus A, one of the brightest radio sources in the sky located 600 million light-years away, displays jets extending 100 kiloparsecs from the nucleus and inflating lobes reaching 150 kiloparsecs total extent. The jets are highly collimated, maintaining narrow widths over vast distances, and carry enormous power, estimated at 10 to the 45th ergs per second. Cygnus A's host galaxy is a giant elliptical showing disturbed morphology with tidal features indicating a recent merger within the past billion years. The connection between merger and jet power suggests the black hole grew through merger-driven accretion, increasing spin and enabling powerful jet launching. The jet launching timescale, several million years after merger based on stellar age gradients in the host galaxy, matches theoretical predictions for disk reformation and spin alignment following binary coalescence. M87's jet, imaged by the Event Horizon Telescope and radio interferometers, including the Very Large Array and Very Long Baseline Array, extends over 5,000 light-years, with substructure resolved down to event horizon scales. The jet exhibits superluminal motion apparent faster than light motion, resulting from material moving at relativistic speeds at small angles to the line of sight. Knots in the jet move at apparent velocities 4 to 6 times light speed, implying true velocities approximately 98% light speed. The jet's base, imaged by EHT, shows a ring-like emission structure with a diameter approximately 40 microarc seconds, corresponding to 5.5 Schwarzschild radii. This size matches predictions for emission from the black hole's photon ring, the innermost stable photon orbit, providing strong evidence that jets originate immediately outside the event horizon, consistent with Blanford's Narjek launching mechanisms. Observable signatures for detection. Detecting supermassive black hole binaries requires multi-wavelength observations covering electromagnetic spectrum, from radio to X-rays and gravitational waves from nanohertz to millihertz. Each wavelength probes different physical processes and spatial scales. Pulsar timing arrays detect nanohertz gravitational waves from binaries at separations 0.001 to 0.1 parsecs, providing the earliest warning of impending mergers years to decades before coalescence. LISA will detect millihertz gravitational waves from the final in-spiral merger and ring-down, observing systems days to months before merger. Periodic quasar variability in optical and X-ray wavelengths reveals orbital periods for binaries at separation 0.001 to 0.1 parsecs. Offset AGN detected through Chandra X-ray imaging with arc-second resolution resolved dual nuclei at separations 100 to 10,000 light-years. Radio VLBI imaging resolves sub-parsec separations, detecting dual compact cores if both black holes launch radio jets. Matthew Graham and collaborators compiled a catalogue in 2015 of periodic quasar candidates, identified through systematic searches of long baseline optical monitoring surveys, including the Catalina Real-Time Transient Survey. The catalogue contains over 100 candidates with periods ranging from 200 days to 10 years and significance levels above 3 sigma. Follow-up spectroscopy and multi-wavelength observations are required to confirm binaries and rule out alternative explanations like accretion disk instabilities or jet precession. Subsequent observations confirmed PG 1302-102 as a strong binary candidate, but found that some other candidates show period evolution inconsistent with binaries or lack additional supporting evidence. The catalogue demonstrates that systematic searches can identify binary candidates, but confirmation requires intensive multi-wavelength campaigns. Dual AGN spectroscopy detects double-peaked emission lines from gas orbiting each black hole in closely separated binaries. When both black holes accrete actively and produce narrow-line emission from gas, in their respective narrow-line regions, clouds orbiting at hundreds to thousands of kilometers per second spectroscopy reveals 2 sets of emission lines Doppler shifted by the binary orbital velocities. For a binary with orbital velocity 1000 kilometers per second, the line splitting is approximately 2000 kilometers per second, well resolved in high-resolution spectroscopy. Observations with ground-based telescopes and the Hubble Space Telescope identified dozens of double-peaked AGN, though interpretation is ambiguous because single black holes with rotating accretion disks or outflows can also produce double-peaked lines. Spatially resolving the 2 emission regions using adaptive optics or VLBI confirms dual nuclei unambiguously. Chandra X-ray Observatory provides arc-second angular resolution, resolving dual AGN at separations 1,000 to 30,000 light-years in galaxies within 1 billion light-years. X-ray emission from hot gas in the accretion disk corona, the region immediately above the accretion disk, where gas reaches tens of millions of Kelvin, is compact, extending only light days from the black hole. Detecting 2 compact X-ray sources in a merging galaxy confirms 2 accreting black holes. NGC 6240, discussed earlier, is the archetypal dual AGN with separation 3000 light-years resolved in Chandra imaging. Future X-ray missions, like Athena, planned for launch in the 2030 seconds, will provide 5 arc-second resolution and far higher sensitivity, detecting dual AGN at cosmological distances and resolving separations down to 300 light-years at 1 billion light-years distance. VLBI radio imaging reaches sub-milli-arc-second resolution by combining signals from radio telescopes distributed across continents or even spanning Earth's diameter, creating a virtual telescope with baseline equal to the separation between telescopes. The Very Long Baseline Array, consisting of 10 25-meter radio dishes distributed across the United States with baselines up to 8,000 kilometers, achieves angular resolution below 1 milliarc-second at 5 GHz, corresponding to linear scale's 3 light-years at 1 billion light-years distance. The Event Horizon Telescope, combining telescopes globally, achieves 20 microarc-second resolution through interferometry at 230 GHz, resolving event horizon scales for nearby supermassive black holes. VLBI detected compact radio cores in several dual AGN candidates, confirming parsecant scale separations. The next generation Very Large Array, proposed for completion in the 2030 seconds, will improve sensitivity by factors of 10, detecting weaker radio jets and resolving dual cores more readily. Gaia astrometry provides another detection method through precise position measurements. The Gaia Space Telescope measures positions of over 1 billion stars and extragalactic sources with precision 10 to 100 micro-arcseconds over its 10-year mission. For nearby AGN, within 300 million light-years, this precision corresponds to linear scales 0.1 to 1 light-years. If an AGN hosts a binary, the photocenter, the brightness-weighted average position, will shift periodically as the binary orbits and accretion variability changes which black hole is brighter. Detecting this photocentric wobble reveals binary orbital parameters. Gaia has measured positions for thousands of AGN. Analysis of position time series is ongoing and might reveal binary signatures in AGN previously considered single based on other observations. The aftermath unified black hole, the final merged black hole, contains 95 to 97% of the initial combined mass, with 3 to 5% radiated as gravitational waves during inspiral and merger. For two 100 million solar mass black holes merging, the remnant mass is approximately 195 million solar masses. 5 million solar masses converted to pure energy in the form of gravitational waves. This mass-energy conversion efficiency of 5% far exceeds nuclear fusion's 0.7% efficiency, making black hole mergers the most efficient energy release mechanisms in the universe, aside from matter-antimatter annihilation. The remnant's exact mass depends on pre-merger spins and mass ratio. Equal mass mergers, with non-spinning components, radiate approximately 5%. Unequal mass ratios reduce radiated energy. The most asymmetric mergers radiate only 2 to 3%. Aligned spins increase radiated energy to 7 to 8%, while anti-aligned spins decrease it. The remnant spin typically reaches Kerr parameter A divided by m between 0.7 and 0.9 for comparable mass mergers. For equal mass binaries with initially non-spinning black holes, all angular momentum comes from orbital motion. When the binary merges, orbital angular momentum converts to remnant spin, yielding approximately 0.69. If both pre-merger black holes had aligned spins, A equals 0.9, vector addition of the two spins plus orbital angular momentum produces remnant spin approaching A equals 0.95, near the theoretical maximum. Misaligned spins reduce final spin if spins are perpendicular to orbital angular momentum. Final spin drops to approximately 0.4 to 0.6. Anti-aligned spins, both spins opposite to orbital motion, produce even lower final spins, around A equals 0.3 to 0.4. Measuring remnant spin through gravitational wave ring-down signals constrains pre-merger spin configurations and tests general relativity's predictions for how angular momentum combines during mergers. Accretion disk reformation occurs over 1,000 to 10,000 years as gas settles into new orbits around the merged black hole. The violent merger disrupts the circumbinary disk and mini-disks that existed before coalescence. Gravitational wave recoil kicks might displace the remnant black hole from the galactic center, carrying it away from the densest gas concentrations. Tidal forces during the final orbits shock heat gas to temperatures exceeding 10 million Kelvin, ionizing it completely and increasing pressure support against gravitational collapse. Over subsequent centuries to millennia, this hot gas radiates energy through Bremsstrahlung and line emission, cooling and falling back toward the black hole. As gas cools below 100,000 Kelvin, it can form molecules and cool efficiently through molecular transitions, allowing gravitational collapse into a new accretion disk. The timescale depends on gas density, metallicity, and the presence of cooling agents like dust grains. Warped disks form if the remnant black hole's spin axis is misaligned with the infalling gas's angular momentum. Gas initially orbits in planes determined by pre-merger geometry, perhaps aligned with the orbital plane of the binary that just merged. But the remnant's spin axis might point in a different direction due to vector addition of pre-merger spins and orbital angular momentum. Differential precession inner disk regions precess faster than outer regions due to stronger frame dragging near the black hole causes the disk to warp. The Bardeen-Peterson effect, predicted by James Bardeen and John Peterson in 1975, describes how viscosity in the warped disk transports angular momentum, causing inner regions to align with the black hole's spin while outer regions retain their original orientation. The alignment timescale is approximately T-align equals h divided by r, all squared times r cubed divided by gm times 0.1 divided by alpha, where h is disk scale height, r is radius, and alpha is viscosity parameter. For typical parameters, inner disk within 100 Schwarzschild radii aligns within 10,000 years. Quasar reignition is delayed 10,000 to 100,000 years after merger as the accretion disk reforms and gas funnels inward to feed the black hole. During this delay, the remnant black hole is quiescent, not accreting significantly and producing minimal electromagnetic emission. The galaxy might show post-starburst signatures, stellar populations, indicating recent intense star formation now ended but no active nucleus. Eventually, gas settles into a stable accretion disk, and accretion resumes, reigniting the quasar. The reignited quasar might be brighter than pre-merger. If the merger increased the black hole's spin to near maximal values, enabling more efficient jet launching and higher radiative efficiency. Alternatively, if the recoil kick displaced the black hole from the galactic center where gas density is highest, accretion might be suppressed, producing a fainter post-merger AGN or no AGN at all if the black hole was ejected entirely. SDSS J1430 plus 2303. A galaxy at redshift Z equals 0.086, corresponding to 1.2 billion light-years, is a candidate post-merger system showing post-starburst stellar populations without current star formation combined with AGN activity. Spectroscopy reveals strong Balmer absorption lines from A-type stars, massive main sequence stars with lifetimes around 1 billion years, indicating a starburst ended roughly 1 billion years ago. Simultaneously, X-ray observations detect an active nucleus with luminosity 10 to the 43rd ergs per second, indicating ongoing black hole accretion. The combination suggests the galaxy experienced a merger, triggering a starburst and black hole growth, followed by AGN feedback quenching star formation, then a delay before AGN reignition. If SDSS J 1430 plus 2303 is indeed a post-merger remnant, it represents the transition phase between merger-driven activity and the quiescent red galaxies that are final merger products. The merger's gravitational waves carry away angular momentum as well as energy. Angular momentum removal affects the remnant's properties. Less angular momentum in the remnant means lower spin. For non-spinning binaries, roughly 30% of orbital angular momentum radiates away, with 70% becoming remnant spin. For spinning binaries, the fraction radiated depends on whether spins align or anti-align with each other and with orbital motion. Aligned configurations radiate less angular momentum proportionally, producing higher remnant spins. Anti-aligned configurations radiate more, producing lower spins. Measuring gravitational wave signals constrains how much angular momentum radiates, testing general relativity's predictions. Deviations would indicate modifications to Einstein's equations or exotic matter distributions near the black holes. The no-hair theorem ensures the remnant quickly forgets details of its formation, settling into a Kerr black hole characterized solely by mass and spin. Perturbations in the event horizon's shape, lumps, bumps, or oscillations created during merger radiate away as gravitational waves during ringdown, which completes within milliseconds. After ringdown, the black hole is in equilibrium, a perfect Kerr solution with axisymmetric geometry, determined entirely by M and A. All information about the pre-merger black holes, their individual masses, spins, orbital parameters, is encoded only in the gravitational waves that escaped. An observer examining the post-merger black hole months later cannot determine how it formed, whether through binary merger, single black hole growth through accretion, or any other process without detecting the gravitational waves or electromagnetic signatures from the event. Accretion resumes once the disk reforms and gas flows inward at rates determined by disk viscosity and gas supply. If abundant gas is available 10 to the 8th to 10 to the 9th solar masses in the central kiloparsec, the black hole can accrete at rates approaching Eddington, sustaining luminous quasar activity for 10 million to 100 million years until gas is exhausted or feedback expels remaining gas. If gas is scarce typical of elliptical galaxies, where mergers occurred billions of years ago and subsequent accretion depleted central gas accretion rates might be far below Eddington, producing low luminosity AGN, like those in many nearby ellipticals, including M87. The Milky Way's Sgr A-star, accreting at only 10 to the -6th Eddington rate, exemplifies a quiescent post-merger remnant. The black hole exists, but accretes minimally due to gas scarcity. Cosmological implications and galaxy evolution. Supermassive black hole mergers trace the history of galaxy mergers across cosmic time. Every major galaxy merger eventually leads to a black hole merger if both galaxies host central black holes and the binary successfully evolves through the final parsec. Observing black hole merger rates at different redshifts, different cosmic epochs, reveals when galaxies merged most frequently. The cosmic merger rate, estimated from galaxy merger observations and theoretical models, is approximately 0.1 to 1 merger per cubic gigaparsec per year at redshift Z, approximately 1, when the universe was 6 billion years old. Merger rates were higher at earlier times, approaching 1 to 10 per cubic gigaparsec per year at Z = 2 to 3, and decline toward the present as galaxy populations age and gas depletes, reducing merger-driven activity. Gravitational wave observations with LISA will measure merger rates directly, testing galaxy formation models. Mass assembly of supermassive black holes proceeds hierarchically through multiple mergers over cosmic history. Black holes begin as seeds of 100 to 100,000 solar masses formed in the early universe around redshift Z = 10 to 20, when the universe was 100 to 500 million years old. These seeds grow through accretion and mergers. Each galaxy merger adds mass from the companion galaxy's black hole. Over billions of years and multiple mergers, black holes grow from 100,000 solar masses to 1 million solar masses by Z = 6. to 10 million solar masses by Z equals 3, and finally to 100 million to 10 billion solar masses by Z equals 0 today. The most massive black holes, exceeding 10 billion solar masses, like TON 618, formed through exceptionally efficient accretion or multiple major mergers in the densest regions where massive galaxies concentrate. Spin evolution depends on whether mergers preferentially align or randomize spins. If accretion from a coherent gas supply dominates black hole growth, spins align with the accretion disk's angular momentum, producing a population of aligned, high-spin black holes with a approximately 0.9. If growth is merger-dominated with random spin orientations, spins add as vectors with random directions, producing lower typical spins around A equals 0.6. Observationally, measuring spins of supermassive black holes is challenging. X-ray spectroscopy of iron fluorescence lines from the innermost accretion disk constrains spin through relativistic line profiles. Lines from gas orbiting near the event horizon are broadened and shifted by Doppler effects and gravitational redshift in patterns depending on spin. Measurements for several dozen AGN suggest typical spins are approximately 0.6 to 0.9, consistent with both accretion and merger growth, but not definitively distinguishing between them. The gravitational wave background detected by pulsar timing arrays in 2023 represents the superposition of all supermassive black hole mergers throughout the cosmic volume. Each individual binary contributes gravitational waves at frequencies determined by its masses and orbital period. The loudest binaries, most massive systems nearing merger, contribute most to the background. Statistical analysis of the background amplitude and spectrum constrains the merger rate, typical black hole masses, and cosmic history of mergers. Preliminary analyses favor merger rates 0.5 to 2 per cubic gigaparsec per year at Z approximately 0 to 2, consistent with galaxy merger models. Future observations, with more pulsars and longer baselines, will measure the background spectrum precisely, potentially detecting individual loud binaries standing out above the background. Contribution to cosmic energy density from gravitational waves is small but measurable. The energy density parameter omega GW, gravitational wave energy density divided by critical density, is approximately 10 to the minus 9th for the nanohertz background from supermassive binaries. This is far below the contributions from matter, omega m approximately 0.3, and dark energy omega lambda approximately 0.7, but comparable to the cosmic microwave background's energy density, omega cmb approximately 5 times 10 to the minus 5th. The gravitational wave background contributes negligibly to cosmic dynamics today, but might have been more significant in the early universe when merger rates were higher and the universe was denser. Detecting the background spectrum across multiple frequency bands, nanohertz from pulsar timing, millihertz from LISA, and potentially microhertz from future detectors, will map gravitational wave contributions across cosmic history. The horizon mass, the largest black hole that could form by redshift z equals 0 through accretion and mergers, is limited by the universe's age and Eddington limited growth rates. Starting from a 100,000 solar mass seed at z equals 20, accreting continuously at the Eddington rate for 13.6 billion years produces a black hole around 10 to the 11th solar masses, 100 billion solar masses. This represents an absolute upper limit. Real black holes accrete episodically, not continuously, and mergers contribute mass but occur infrequently. The most massive observed black holes are around 60 to 70 billion solar masses, approaching but not exceeding the horizon mass. The absence of black holes above 100 billion solar masses, despite predictions they should form if accretion were continuous, suggests that feedback regulates growth, preventing unlimited mass accumulation. Supermassive black hole demographics, the mass function describing how many black holes exist at each mass, evolves with cosmic time. At high redshift Z greater than 6, black holes are predominantly 100,000 to 10 million solar masses, reflecting recent formation from seeds with limited growth. By Z, approximately 2, the peak shifts to 10 million to 100 million solar masses as mergers and accretion build mass. Today at Z equals 0, the mass function peaks around 1 million solar masses for typical galaxies, with a tail extending to 10 billion solar masses in giant ellipticals. Gravitational wave detections will sample this mass function directly, LISA detecting mergers of 100,000 to 10 million solar mass black holes across Z equals 0 to 10, pulsar timing arrays detecting 100 million to 10 billion solar mass mergers at Z equals 0 to 3, comparing observed mass functions with predictions, tests, black hole formation, and growth models. The M-sigma relations evolution provides clues about co-evolution. At high redshift, the relation shows more scatter, and possibly different normalization black holes might be more massive relative to galaxy bulge masses in the early universe, suggesting black holes grew faster than galaxies initially. By Z approximately 1, the relation tightens, indicating synchronized growth. Today, the relation is very tight, with only 0.3 dex scatter, implying black hole and galaxy growth are closely regulated through feedback. This evolution suggests that AGN feedback became increasingly important over cosmic time as black holes grew massive enough that their feedback energy could overcome galactic binding energies, regulating subsequent growth and producing the tight correlation observed today. Multi-messenger astronomy observations. Multi-messenger astronomy combines electromagnetic observations, gravitational waves, and potentially neutrinos to study supermassive black hole mergers comprehensively. Each messenger provides unique information. Electromagnetic emission reveals gas content, accretion physics, jet properties, and host galaxy environment. Gravitational waves measure black hole masses, spins, orbital parameters, and distance independently of electromagnetic assumptions. Neutrinos, if produced in gas-rich mergers through proton-proton collisions in jets or accretion disk coronae, would constrain hadron acceleration mechanisms and jet composition. Coordinating observations requires establishing memoranda of understanding between gravitational wave observatories, like LISA, and electromagnetic facilities, ensuring rapid follow-up when merger candidates are identified. Early warning from LISA provides a revolutionary capability. For supermassive black hole mergers with total masses 100,000 to 10 million solar masses, LISA detects signals days to years before coalescence, depending on mass and distance. A 1 million solar mass equal mass binary at 1 billion light-years enters LISA's sensitivity band roughly 1 year before merger, when gravitational wave frequency reaches 0.1 MHz. As the binary inspirals, frequency increases, signal-to-noise ratio grows, and sky localization improves. 1 month before merger, sky position is constrained to roughly 10 to 100 square degrees, enabling targeted electromagnetic searches. 1 week before merger, localization improves to 1 to 10 square degrees. This advance notice allows scheduling observations on the world's largest telescopes, preparing for the merger event. Target of opportunity programs on optical, X-ray, and radio telescopes will respond to LISA alerts by imaging and monitoring merger candidates. Optical surveys, like the Vera-C, Rubin Observatory's legacy survey of space and time, will provide continuous, all-sky monitoring with 3-day cadence, detecting any transient optical emission from mergers. X-ray observatories, like Athena, launching in the 2030 seconds with large collecting area and wide field of view, will observe merger candidates searching for flares or brightening as mini-disks disrupt and gas shocks during the final orbits. Radio telescopes, including the Square Kilometre Array and next-generation Very Large Array, will image merger fields at high resolution, searching for compact radio emission from jets or synchrotron flares. Coordinated campaigns maximize scientific return by capturing electromagnetic counterparts across all wavelengths. Localization precision determines whether electromagnetic follow-up is feasible. LISA's constellation geometry provides excellent sky localization for high signal-to-noise detections. For a 1 million solar mass merger at 1 billion light-years with signal-to-noise ratio 100, typical for LISA, sky localization is roughly 1 square degree at 90% confidence. This is sufficiently precise that wide-field telescopes can image the entire error region in single pointings or mosaic observations. For low signal-to-noise detections, faint distant mergers or low-mass systems localization degrades to 10 to 100 square degrees, still manageable but requiring more extensive observations. Ground-based gravitational wave detectors like LIGO have poorer localization, typically hundreds to thousands of square degrees for stellar mass mergers, making electromagnetic follow-up challenging unless multiple detectors provide triangulation. Scientific yield from multi-messenger observations is enormous. Gravitational waves measure mass and spin with 1 to 10% precision, independent of distance uncertainties that plague electromagnetic observations. Identifying the host galaxy through electromagnetic observations provides redshift, determining distance and enabling cosmological tests. Comparing gravitational wave distance, inferred from signal amplitude assuming general relativity, with electromagnetic redshift tests, cosmic expansion history, and dark energy properties independently of traditional distance ladder methods. Detecting electromagnetic counterparts constrains gas content, accretion rates, and merger environments. Measuring jet properties and post-merger AGN activity reveals how black hole spin and accretion geometry respond to mergers. Each multi-messenger detection provides vastly more information than either messenger alone. Neutrino production in supermassive black hole mergers remains speculative but possible. If ultra-high energy cosmic rays protons accelerated to 10 to the 18th to 10 to the 20th electron volts are accelerated in jets or accretion disk coronae, proton-proton collisions produce pions that decay to neutrinos. The neutrino luminosity depends on proton acceleration efficiency and target photon density. For luminous quasars with jet powers 10 to the 47th ergs per second, neutrino luminosities might reach 10 to the 45th ergs per second in the TeV to PeV energy range. IceCube Neutrino Observatory at the South Pole detects neutrinos through Cherenkov light from charged particles produced in neutrino interactions in Antarctic ice. KM3 NITI in the Mediterranean serves similar purpose. Both observatories have detected high-energy astrophysical neutrinos, but have not yet definitively associated any with supermassive black holes. Multi-messenger observations combining neutrino detections with gravitational wave and electromagnetic signals would conclusively identify sources. Coordinated observations face logistical challenges. LISA's gravitational wave alerts will arrive continuously as binaries evolve through the final year before merger. Electromagnetic facilities have limited observing time, major telescopes are oversubscribed with competing programs. Establishing trigger criteria for target of opportunity observations requires balancing scientific value against resource allocation. High signal-to-noise LISA detections of nearby mergers within 1 billion light-years warrant extensive follow-up, potentially displacing other scheduled observations. Low signal-to-noise detections or very distant mergers might receive only minimal follow-up or be monitored solely by all-sky surveys. Community agreements and predefined policies will ensure smooth coordination when mergers occur, maximizing scientific return while respecting existing observational commitments. Future missions to study mergers. LISA, the Laser Interferometer Space Antenna, represents the flagship space-based gravitational wave mission launching in the mid-2030s. The mission consists of 3 spacecraft forming an equilateral triangle with 2.5 million kilometer sides, following Earth in heliocentric orbit about 50 million kilometers behind. Each spacecraft houses 2 telescopes and free-floating test masses, gold-platinum cubes, acting as inertial references. Laser beams measure distances between test masses on different spacecraft with picometer precision, trillionths of a meter. Gravitational waves passing through the constellation modulate these distances by femtometers, detectable through laser interferometry. LISA's frequency band, 0.1 MHz to 100 MHz, is optimized for supermassive black hole mergers, with total masses 100,000 to 10 million solar masses, extreme mass ratio in spirals, and galactic compact binaries. The mission is jointly led by ESA and NASA, with ESA providing spacecraft and NASA contributing scientific instruments and launch support. Taiji, a proposed Chinese gravitational wave mission, follows a similar concept, with 3 spacecraft forming a triangle with 3 million kilometer sides. Taiji's slightly larger constellation provides different frequency sensitivity, optimized for slightly lower frequencies and more massive black holes. The mission timeline targets launch in the 2030s, potentially before or contemporaneous with LISA. Taiji's scientific goals overlap with LISA's, but extend to detecting intermediate mass black holes and possibly primordial gravitational waves from the early universe. Having 2 independent space-based detectors operating simultaneously would provide redundancy, improved sky localization through triangulation between constellations, and confirmation of detections through independent measurements. Coordination between Taiji and LISA is being discussed to maximize scientific return and minimize duplication. Tianqin, another Chinese mission concept, uses a geocentric orbit rather than heliocentric. 3 spacecraft orbit Earth at altitudes approximately 100,000 kilometers, forming a triangle with 170,000 kilometer sides. The smaller constellation size makes Tianqin sensitive to higher frequencies, around 0.1 MHz to 1 Hz, accessing different source populations including intermediate mass black holes and stellar mass compact binaries. Geocentric orbit simplifies operations. Spacecraft remain in Earth's vicinity rather than trailing far behind, but introduces additional noise sources from Earth's gravitational field and requires active drag compensation. Tianqin's launch target is the late 2030s. Its complementary frequency range fills gaps between LISA's lower frequencies and ground-based detectors' higher frequencies, providing complete gravitational wave coverage across 9 orders of magnitude in frequency. The Einstein telescope, a proposed European ground-based detector, will use triangular configuration with 10-kilometer arms constructed in underground tunnels to reduce seismic and gravity gradient noise. The Einstein telescope improves on current LIGO and Virgo sensitivity by factors of 10 across frequencies 1 to 1000 Hz, detecting stellar mass black hole mergers to redshifts to Z approximately 20 and neutron star mergers to Z approximately 2. While unable to detect supermassive black hole mergers due to low-frequency seismic noise below 1 Hz, Einstein telescope will detect intermediate mass black holes of 100 to 10,000 solar masses, bridging stellar and supermassive populations. The detector's underground location in Sardinia, Italy, with tunnels 200 to 300 meters deep, isolates it from surface vibrations and temperature variations. Construction might begin in the late 2020 seconds, with operations starting in the 2030 seconds. Cosmic Explorer represents the next generation ground-based detector for the United States, featuring 40-kilometer arms, 4 times longer than LIGO's 4-kilometer arms. The longer baseline provides correspondingly better sensitivity, detecting stellar mass mergers to the edge of the observable universe at Z approximately 100 if such systems exist. Cosmic Explorer's sensitivity at 10 to 100 Hz enables precision tests of general relativity through ring-down measurements and tidal deformability measurements, constraining neutron star equation of state. The detector will be constructed at a U.S. site, yet to be determined, possibly in existing LIGO facilities with arms extended or at entirely new locations. Funding and construction timeline are under discussion, with operations potentially starting in the 2040 seconds. Cosmic Explorer and Einstein Telescope together form a global network, providing all-sky coverage and triangulation for localizing sources. Athena, the Advanced Telescope for High-Energy Astrophysics, is an ESA X-ray observatory launching in the mid-2030 seconds, with collecting area 2 square meters, 10 times larger than current X-ray missions, and angular resolution 5 arcseconds. Athena will detect supermassive black hole mergers through electromagnetic counterparts, X-ray flares from gas shocks, brightening from accretion rate changes, and evolving ion line profiles from warped disks. The Wide Field Imager provides 40 arc-minute field of view with spectral resolution enabling redshift measurements. The X-ray Integral Field Unit provides high-resolution spectroscopy measuring gas, velocities, densities, and temperatures in AGN. Athena will observe LISA merger candidates, providing host galaxy identifications, redshifts, and accretion physics. Joint LISA-Athena observations maximize multi-messenger science, combining gravitational wave masses and spins with electromagnetic accretion diagnostics. The Next Generation Very Large Array, NGVLA, will provide radio interferometry with baselines spanning North America, achieving 10 times better angular resolution than the current VLA. Operating at frequencies 1 to 116 GHz, NGVLA will image jets, compact radio cores, and circumnuclear gas with resolution below 1 milliarc second, corresponding to light-year scales at cosmological distances. NGVLA will detect dual AGN at parsec separations, resolve jet launching regions, and measure black hole masses through molecular gas kinematics. For LISA merger candidates, NGVLA will search for radio counterparts from jets or synchrotron flares. The array consists of 244 antennas, 214 dishes across the continental United States, 19 inches northern Mexico, and 11 clustered for short baselines. Construction is planned for the 2030 seconds with full operations by 2035. The Square Kilometre Array, SKA, represents the world's largest radio telescope with collecting area 1 square kilometre distributed across thousands of antennas in South Africa and Australia. Sgr operates at frequencies 50 MHz to 14 GHz, providing sensitivity orders of magnitude better than existing radio telescopes. For gravitational wave science, Sgr will improve pulsar timing, precision, detecting individual supermassive black hole binaries above the nanohertz background. Sgr will monitor 1000 millisecond pulsars with timing, precision below 10 nanoseconds, resolving the gravitational wave background into discrete sources and measuring individual binary parameters. Sgr Phase 1, currently under construction, begins operations in 2027. Phase 2, completing full square kilometer collecting area, follows in the 2030 seconds. Coordinating this suite of future missions requires international collaboration and data sharing. Memoranda of understanding between gravitational wave and electromagnetic facilities establish protocols for rapid follow-up, data access, and publication policies. LISA will publicly release merger alerts with sky positions and parameter estimates, enabling electromagnetic observers to point telescopes rapidly. Electromagnetic facilities will share observations through centralized databases, accessible to gravitational wave teams for correlation and analysis. This open science approach maximizes community participation and scientific return, ensuring that supermassive black hole mergers are studied comprehensively across all messenger types by the global astrophysics community. What it means for the universe's fate. Eventually, all galaxies within the local group will merge as gravitational attraction overcomes cosmic expansion on scales smaller than 10 million light-years. The Milky Way and Andromeda will collide in 4 billion years, followed by mergers with smaller galaxies like Triangulum and the Magellanic Clouds over subsequent billions of years. Each merger adds stars and gas, building the final merged remnant Milky, a giant elliptical galaxy containing the combined stellar mass of the local group, roughly 2 trillion stars. The supermassive black holes from each galaxy will sink to Milky's center through dynamical friction, forming binaries that eventually merge. The Milky Way's 4 million solar mass black hole and Andromeda's 100 million solar mass black hole will coalesce around 6 to 7 billion years from now, creating a 104 million solar mass remnant after radiating a few million solar masses in gravitational waves. Smaller black holes from dwarf galaxies add modest mass, bringing the final central black hole to approximately 110 to 120 million solar masses. The merger timescale for the Milky Way and Andromeda black holes is approximately 1 to 2 billion years after the galaxies collide. Initial galactic contact occurs when disk components overlap around 4 billion years from now. The supermassive black holes begin at separations around 100,000 light-years, the approximate distance between galactic centers after first pericentric passage. Dynamical friction brings them together over 500 million to 1 billion years, reaching separations around 1 to 10 light-years. The final parsec problem might delay merger at parsec scales for 10 million to 100 million years, until triaxiality, gas torques, or stellar scattering drive the binary to gravitational wave-dominated regime. The final inspiral from 0.01 parsecs to merger lasts roughly 10 million years, with gravitational wave frequency sweeping through nanohertz to millihertz over the final year. The merger itself occurs in milliseconds, producing a 104 million solar mass remnant spinning at Kerr parameter A, approximately 0.7 to 0.9. Dark energy continues accelerating cosmic expansion, isolating the local group from increasingly distant structures. Galaxies beyond 10 to 20 million light-years recede faster than light due to space expansion, crossing the cosmic event horizon beyond which they become forever unreachable. The Virgo cluster, currently 54 million light-years away and part of the Virgo supercluster containing the local group, is receding at roughly 1,200 kilometers per second. Over billions of years, Virgo accelerates away, eventually disappearing beyond the horizon. Eventually, all external galaxies cross the horizon. Observers in Milky Way 100 billion years from now will see only their own galaxy in an otherwise empty black universe. They will have no observational evidence that other galaxies exist or that the universe underwent a Big Bang. All evidence will have receded beyond reach. Heat death occurs at timescales around 10 to the 14th years, 100 trillion years, when the last stars exhaust nuclear fuel. Stars forming today from remaining gas will burn for trillions of years if they are low-mass red dwarfs. Once gas is exhausted and star formation ceases around 100 trillion years from now, existing stars slowly die. Red dwarfs, the longest-lived stars, exhaust hydrogen over 10 trillion years, becoming white dwarfs. By 100 trillion years, essentially all stars have died, leaving galaxies populated by stellar remnants, white dwarfs, neutron stars, black holes. Galaxies themselves evaporate through gravitational interactions, ejecting stars to infinity, occurring on timescales 10 to the 19th to 10 to the 20th years. The universe becomes cold, dark, and diffuse stellar remnants and black holes separated by ever-increasing distances as expansion continues. Hawking evaporation ensures even black holes are mortal, evaporating over incomprehensibly long timescales. A 100 million solar mass black hole, like Milky Way's central black hole, evaporates through Hawking radiation in approximately 10 to the 98th years. The evaporation timescale is proportional to the cube of the mass, so less massive stellar black holes evaporate faster. A 10 solar mass black hole evaporates in 10 to the 67th years, though still far exceeding the current universe's age of 13.8 billion years. As black holes evaporate, their temperature increases inversely with mass, accelerating evaporation. The final moments before complete evaporation see the black hole becoming microscopic and extremely hot, radiating the last mass in a burst of gamma rays over microseconds. After the last black holes evaporate around 10 to the 100th years, only radiation and perhaps stable particles like electrons and positrons remain, infinitely dispersed through expanding space. Proton decay, if it occurs as predicted by some grand unified theories, accelerates the universe's dissolution. The standard model of particle physics assumes protons are stable, but grand unified theories predict decay with lifetimes around 10 to the 34th to 10 to the 36th years. If protons decay, all atomic nuclei eventually disintegrate. White dwarfs, composed of carbon and oxygen nuclei, dissolve into radiation and leptons over 10 to the 36th years. Neutron stars, if they survive that long without collapsing to black holes or evaporating through exotic processes, also decay. By 10 to the 40th years, if proton decay occurs, no atomic matter remains, only radiation, leptons, and black holes. Experiments searching for proton decay have not observed it, despite sensitivities reaching 10 to the 34th year lifetimes, suggesting either protons are stable or decay timescales exceed current experimental limits. The final moments for Milky Way's black hole occur when it evaporates completely approximately 10 to the 98th years from now. By this epoch, the universe is unrecognizably different from today. Cosmic expansion has diluted matter and radiation densities to near zero, Temperature approaches absolute zero, perhaps 10 to the minus 30th Kelvin. The black hole, the last significant mass concentration in the local group's descendant region, has shrunk from 110 million solar masses to microscopic size. Its final evaporation releases energy equivalent to roughly 10 to the 8th solar masses in a burst of Hawking radiation, gamma rays, and particles propagating through the vast, empty cosmos. This burst is the last significant energy release in the local group's region. Afterward, only diffuse radiation remains, redshifted to infinitely long wavelengths, effectively carrying zero energy. The region becomes indistinguishable from the cosmic background, cold, dark, and empty forever. Future civilizations within Milky Way, if they exist billions of years from now, will observe a universe fundamentally different from ours. They will see no external galaxies, all have receded beyond the cosmic horizon. The cosmic microwave background will have redshifted to undetectable wavelengths, erasing evidence of the Big Bang. Without external reference frames or cosmological observations, they might conclude the universe is static, eternal, and consists only of their galaxy. They will have no way to discover cosmic expansion, dark energy, or the universe's beginning unless they detect gravitational waves from ancient black hole mergers or find records left by earlier civilizations. This illustrates how cosmic horizons' limit knowledge observations are fundamentally restricted to accessible regions, and as the universe expands, those regions shrink, eventually isolating each galaxy-sized region into a separate observable universe unaware of others. Supermassive black hole mergers represent pivotal moments in cosmic history, events where gravity reaches its theoretical limits, releasing energy exceeding all starlight combined, reshaping galaxies, and producing gravitational waves detectable across the universe. They trace galaxy evolution, revealing merger histories and growth mechanisms. They test general relativity in extreme regimes inaccessible by any other means. They connect black hole growth to galaxy formation through feedback regulating star formation and gas content. Understanding these mergers requires multi-messenger observations, combining gravitational waves and electromagnetic signals across wavelengths and timescales from seconds to billions of years. The coming decades, with LISA, pulsar timing arrays, and next-generation telescopes, will transform supermassive black hole mergers from theoretical predictions to routine observations, unveiling the universe's most energetic collisions and revealing how galaxies and black holes co-evolve across cosmic time.